for being here to this cycle of conference that we wanted actually to organize 5 years ago, but there was some repulsion forces that made that this was only possible to happen now. So there are basically 6 different type of successive conferences. One is about statistical physics. I'm sorry, we cannot read very well. The second one is more about asymptotics, and then it will move more into application and modeling data to biology. So this week we are going to be mainly focused on this probabilistic method and statistical physics for extreme statistics and rare events that we organize with Gregory. And actually, I have to thank Gregory because he did most of the work to gather all of you. So I wanted first to thank him. And also to the De Giorgi Center for giving us the possibility to do that here. The director, Stefano Marmi, and Luigi Ambrosio, that also suggested and proposed to organize that here. So I just want to give you 2 more things. For all the part that has to do with the administration, I remind you that Katarina is the person, plus the person I will mention in the next slides. For the sponsor, most of the money comes from the De Giorgi Center, from the French CNRS, and we got also some money from the French-Italian, and possibly Gregory will mention that, French-Italian University, and also from the Biophysical Society. So some final remarks. So most of the talks will be video recorded, and so I guess you have to sign the form, so please see when to do that, probably before giving the talk. We will have Friday, free afternoon on Friday, and we'll have a restaurant at night, so please check with us where the restaurant will be organized so that you know where to go. And finally, starting from tomorrow, for the students, I will try to give 1 hour class, maybe 45 minutes, about basics of how to go from mean first passage time to the apply mass formulation, and how to do asymptotics to get formula. So this is mainly for the students, but if you're interested, you're welcome, of course, to attend. So for all the administration, I refer you to Antonella and Luisa. That, you know, Luisa is here too at the reception. And again, Katarina for any financial and administrative issues. Okay, so this is what I wanted to say. I hope we'll have an interesting week. The idea is to have all of us together to foster collaborations, exchange ideas, and I'm looking forward to this week.
Okay, so good morning, everybody, and I would first like to thank David and Gregory for organizing this meeting, and also, you know, to all of you for coming here. I'm sure it's going to be a nice week. So I'm going to talk about universal statistics of records. And this is sort of based on some recent work that we did with Claude Godrèche, Joachim Krug, Gregory Scher, and Philippe von Bohmbad, who was a master student of Joachim. And so my talk is going a little bit up. Okay? Okay. So, right. So here is the outline of my talk. So my talk is going to be divided into 2 parts. So I'll first start with a very general introduction to record statistics. Some of you may not be familiar with it. And this will be sort of based on some recent review that we wrote with Claude Godrèche and Gregory Scher. And it's a topical review in this. I'm not sure I can cover everything, but just as an introduction basically. And in the second half, I'll talk about a more recent, a simple model for rainfall precipitation records, which turns out to be exactly solvable. And this is a sort of recent work done with Philipp von Bohmard and Joachim Krug, which has appeared in the archive 2 weeks back. Okay, so let me start with just basic introduction. So extreme events, actually they are not that much rare. As we speak along right now, there are typhoons and there are hurricanes in US and Asia and everywhere, and you have earthquakes. So these are events that are happening all the time, and of course they are devastating. And so one way to characterize such extreme events is through their record statistics, which is particularly, public is particularly perceptive to these record statistics. For example, if there is an earthquake, if you say it has a magnitude of 8 on the Richter scale, it doesn't register that much. But if you say this is the record earthquake, which means it has never happened before, somehow people get interested in this. And so record statistics do play sort of major role in public perception. And in fact, this you can see from the fact that Guinness Book of World Records happens to be the world's best-selling book. And because people are just, human beings are, naturally curious about records. And we hear records all the time. In the television, in sports, in climates, in finance, everywhere this is always talking about record prices, record temperatures, record rainfall, etc. Okay. And so just because we are in Italy, so I'm obliged to show you the world's record pizza, which is, of course, not in Italy. It's in somewhere in the US, and you need a crane to lift this pizza. And then there are these, for example, whenever the economy of a country gets stronger, they try to build towers, and you have more record and record towers, which is going up in time and so on. So and this is the sort of real data of rainfall from Blake Garden. And again, you can see these are the record rainfall, which means record means that that has not happened before. So this is the biggest so far. So it's current maximum essentially. So it goes on. So for record statistics has played a very important role in climates, as I'll come along discuss later. And so basically we are talking about is that imagine that you have a time series xi versus I. It can be anything. It can be a time series of finance, stock price, or it can be temperature records, temperature data, and so on. And so we say that record happens at step k, for instance here, if the value there xk is bigger than all other previous values. Okay, so that's the definition of record. Okay, and so in other words, xk, the current value, is bigger than the current maximum. So maximum of all the previous values. So it's like a current maximum, which is changing with time. And so if this is the the new maximum, then we say that a record happens here. Okay. So what are the questions? So general question is the following. General problem is the following. So imagine that you have a time series and with entries like x1, x2, x3, xn. And imagine that they are drawn from some joint distribution, which could be independent, uncorrelated, or it could be correlated. Okay, if it is uncorrelated, then this just factorizes into individual distributions. Otherwise, in general, it may be correlated. So imagine that you give me this joint distribution. Okay, so you have these random variables you draw from this joint distribution, and then you can ask, okay, how many records? So for example, if Rn denotes the number of records in step n. In this example, you have 1, 2. They are shown by red dots. 1, 2, 3, 4, 5, and this is a record because this has not happened before. This is a record, but this is not a record, of course. Okay. So the question generally is, given this joint distribution, what can I say about the statistics of this random variable Rn, which is his total number of records up to step n. Okay. And then you can ask other questions like, how long does a record survive? So imagine that you have a record happens here. How long is it going to survive? Okay, so what are the ages of the records? So L1, L2, L3, etc. They denote the ages, that is the distance, time distance between two successive records. You can ask for the longest or the shortest record, that is the record whose age is the maximum, the longest surviving record, or the shortest surviving record, and so on. So you can ask many interesting questions about these record statistics. So the general problem is this, okay? So you somehow or the other, this joint distribution, and you want to compute these objects, okay? So that's the sort of general problem. And why does it sort of appear in other places apart from statistics and so on, is because this is also a very it appears in many different physics problems, including elastic line moving in a disordered medium and vortex density in type 2 superconductors and spin glasses, then evolutionary models that Joachim is going to talk about next. And then you have the rainfall records that I'll talk about. So basically what happens is that you have this record, these time series. So you have this time series in the blue curves basically. And the record, so this is a record and then it stays record. This is not a record. So the record value, if you plot the record value, it stays flat and then it jumps, a new record happens and then it stays for a while flat because these guys are not records. And then it jumps. So it's a plot of the current maximum as it's changing. So once in a while it jumps and so on. So it has this staircase structure. And this kind of staircase structures appears in, as I said, many problems like this. So let me just give you one example. So imagine that you have a disordered line, elastic line like a polymer in a disordered medium. So these are the red dots are the disordered basically. Then you are pulling this polymer by some force, and this is a picture I stole from the article by Alberto Rosso and Christoph Texier. And so you pull them by a constant force. And then what happens is that and just monitor the center of mass. So center of mass actually gets stuck for a while, and it doesn't move. And then when the time exceeds for a longer time, then it jumps, and then again stays there and jumps. So this is just the plot of the mean position along this line as a function of time. Okay? So once again, you see these staircase structures, and so therefore these staircase structures, they're often modeled by the record statistics because they have the exactly similar sort of statistics. So records, has been used in many things. I mean, sports, and then evolution models in biology. So Joachim has worked quite a lot on this. Disordered systems, spin glasses and avalanches. So in fact, I mean, these are like the little avalanches here, and big jump basically. It moves, suddenly it moves, and so there is a big avalanche. So the jump here is like an avalanche. And then growing networks. Claude Godrèche and Jean-Marc Luc had worked on this. And then you have this lot of articles on global warming. These days it's a very hot topic because global warming you can study by records. I'll come back to that a little bit later. And so many different areas the records have been studied. And in fact the classical theory of records, which has been studied for a while now, almost more than 60 years, which assumes that the underlying time series has independent and identically distributed continuous entries. I'll come back to that more later. And it turns out that the whole statistics of records is totally universal in the sense it doesn't depend on the distribution of the entry that you pick up your random variables from. And so this is the classical theory of records, and I'll review this in more detail in a minute. And whereas much less is known about record statistics for correlated time series, such as random walks and Levy flights and so on. These are time series are correlated, and it turns out that even there. There is universality, and there has been some work on this in the last few years. And but this universality is for a different reason than the universality here. But okay, maybe today I'm not going to talk much about the correlated time series. We'll come back to that later if I have time. Okay, so let me just start from the records for IICD, the independent, identical, continuously distributed random variables, and let's see simply that what can we say about the statistics of records there. Okay. So it's actually very simple. So as I said, the joint distribution. So I have the entries, random variables x1, x2, x3, xn, and their joint distribution is a product of the individual marginal distributions. And I'm going to assume that this is a continuous PDF. Okay, so you give me this p of x, and now I want to first calculate the number of records. Okay, so I look at up to step n. So Rn is the total number of records, total number of red dots that occurs. So it's convenient to introduce this binary variable sigma k, which if you say that at step k, if there is a record, if there is a red dot, I put it 1, otherwise I put it 0. Okay? So if I know this binary variable for a given realization, then the sum of these binary variables is just an indicator function. So that is just the total number of records up to step n. Okay? So the average number of records, for example, up to step n, so I take an average over this. So this is the average over sigma k, sum over k, and this sigma k average Rk is just a probability that a record happens at step k. So sometimes it's called the record rate. Okay. So if I know this, the statistics of sigma k, essentially I know the statistics of Rn. So let's see what can we say about the average number of records. So Rk, I want to calculate this Rk because if I sum over k, then this is the average number of records. So this is the probability that a record happens at step k. Okay? So that is the probability. The event is that xk, the value there should be bigger than all the previous values, right? So if you compute this, it's very simple to see that this will be 1 over k, irrespective of the distribution p of x, as long as it's continuous. And the reason is, very simply, is because, I mean, what is the probability that this is a record? That means what is the probability that this guy is the maximum out of these k entries? And because they are IID variables, so therefore the probability that this is the maximum, any one of them can be maximum, they have equal probability. So the probability that the last guy is the maximum is just 1 over k. And if you are not convinced, you can do a little calculation. I'll do it in a minute. So, but the point is that this is totally universal, the average number of records. It's independent of the underlying distribution p of x. Okay? So you can take Gaussian, you can take uniform distribution, you can take exponential. Everybody will give you the same answer, 1 over k. And mathematically the proof is very simple. So Rk, you want to calculate what's the probability that this is a record. So let's say its value is xk. Probability for that is p of xk. And I have to ensure all the previous guys are less than xk because they are independent. So it's just a px dx integral minus infinity to xk. And you have to raise it to the power k minus 1 because they are independent and all of them have to be less than xk. Now this integral here is very simple because you just make a change of variable u equal to minus infinity to x px dx. And then, so this, what this change of variable does is that it changes to any continuous distribution to uniform distribution between 0 and 1. Okay? And then immediately you see that this will be 1 over k. So the universality here comes from the fact that all these IID distributions, all of them, I mean, you can actually map it to essentially uniform distribution between 0 and 1. So that's the sort of key to the universality. Okay? So once you have that, so average number of records is therefore just sum over Rk, which is just 1 for any n, it's universal, and it's 1 plus half plus up to 1 over n, which of course for large n goes like log n. But it's actually universal for all n, not just for large n. Okay, so this is the average number of records. So how about higher moments? So the point is that, so let's calculate, for example, just the 2-point function. What is the sigma k, sigma j? Sigma j, remember, is the indicator variable. So if j is bigger than k, for instance, I mean, then this is just the probability that this guy is a record and that guy is a record. Okay, both records. And you can again do these same calculations. What I have to do is I have to fix this guy at value xj and that guy at value xk. And then all these guys before this guy should be less than xj. And there are j minus k minus 1, these guys here. And similarly, this guy, all the guys before it should be less than xk, which is to the power k minus 1. It looks a little bit complicated, but it's not complicated. Once you make this change of variables, you immediately reduces to just a uniform distribution, and again you see that this is totally universal, and it's just the answer is 1 over k times 1 over j, which is actually the product of sigma k average, sigma j average. So what you see is that the 2-point function totally factorizes into 1-point functions, and therefore there is absolutely no correlation between this sigma j and sigma k. So these record occurrence variables, sigma k's, they are totally uncorrelated. And so this is the sort of main thing that you get from the independent and identically distributed continuous variables for j not equal to k. Of course, for j equal to k, sigma square is sigma, so it's just a mean value. Okay, so they get totally uncorrelated, and consequently you can calculate the variance. So variance is just because they are uncorrelated, is just the summation sigma k square minus sigma k average square. You can calculate, and this is an exact answer for all n. And again, it's totally universal. And it goes again like log n. Okay. So one thing that you can compute from this, which is useful, is in statistics is called the Fano factor, which is the variance over the mean. Okay. So Fano factor tells you, for if you have a Poisson distribution, it's actually exactly 1. So originally in mesoscopic physics, Fano factor was derived just to show the deviation from Poisson statistics. Now, if these record rates are completely independent, completely uncorrelated, then you can just calculate this as we just did, and it's a simple function like this, and you can prove that this is a monotonically increasing function of n. Okay, so as long as your sigma k variables are uncorrelated, this is always monotonically increasing function of n. As n goes to infinity, it approaches to 1 very slowly here. Okay, so this is the mean and variance. how about the record number distribution, okay, full distribution. So now full distribution is also universal, and to see this, you see that Rn is summation sigma k, and so the probability that a record occurs at step n, say, is just 1 over n, and we have seen that these sigma k variables are totally uncorrelated. So these are independent events. Like each time step with probability 1 over n, there is a record which occurs. Okay, so it's like a Poisson process basically. So therefore, you can write down the evolution equation probability of having R records in step n. It satisfies the Markov master equation. So it's simply P of Rn at step n. If I have R number of records, then at step n minus 1, maybe I had R number of records, which means that at the step n there is no record. The probability for that is 1 minus Rn. Or at the previous time step, I had R minus 1 records, and then one record happened at step n minus 1, and that's the probability Rn. And so it's just a simple master equation. So you can see from here you can solve exactly in terms of Stirling numbers. I'll not. This was done a long time back. And this is, so you can see that the full distribution is again universal, that is independent of P of x. So in fact, I mean, you can analyze for what happens for large n, and large n you can show very easily that it converges to a Poisson distribution. And with this factor is just analyzing this exact solution. And in particular, near its mean, the Poisson sort of becomes the Gaussian. And so the typical fluctuations of our Gaussian distribution, and you can see that obviously because of central limit theorem, because R is summation sigma k, they are uncorrelated. So obviously the typical fluctuations will be described by the central limit theorem to be Gaussian with this mean and the variance. Okay, so this is the sort of mini review of independent and continuous distribution variables, but it has many applications. In particular, the fact that the number of records in this IICD sequence of size n, it turns out to be exactly same as the number of cycles in a random permutation of n integers, and this is also well known. And there are many other physical models where this fact has been used, growing network models and ballistic aggregation model, and this age statistics of records, and some of these you can find in this review. I'm not going to the details of this. Okay, so now this fact that it's totally universal of the record statistics, this has been very useful, in particular in climatology. This universality of record statistics, so for instance, I mean, whenever you have a universal statistics, in statistics you can. This is very useful because you can use it as a sort of distribution-free test for a null hypothesis. So imagine that you make a null hypothesis that your underlying random variables are totally uncorrelated, and then you want to test this. One way to test this is if you look at the record statistics, and you don't know the underlying distribution. So the record statistics, the fact that it doesn't depend on the underlying distribution. So if you find the record statistics to be given by this universal behavior, then you know that the underlying variables are IID variables. So this is like what is called the Kolmogorov-Smirnov test. That's another test for which is used heavily in statistics. So this is a sort of similar distribution-free test. That means you don't need to know the underlying distribution. You can just check if they are independent or not. And this has been used for example, temperature records. And it has motivated a lot of recent studies on global warming by studying the frequency of temperature records. So there's a lot of work here. I'll not go into the detail. And in comparison to temperature records, there were relatively less studies on the statistics of rainfall records or precipitation records. And this is what I'm going to talk about now in this second half of my talk. And so what we'll do is that we'll study a particular model of rainfall, which is just a generalization of this IICD model, as you will see. And it turns out to be again exactly solvable, and again it's totally universal. And this is a sort of somewhat realistic model of rainfall records, and the fact that it's exactly solvable is quite nice. Okay, you can use it as a sort of null hypothesis again for rainfall records. Okay, so what is the rainfall record and temperature record? So imagine that, okay, I'll just give you a simple example, a schematic example. So imagine that you have a calendar day, let's say 1st of July every year, okay? And let's say you have a time series for, let's say, temperature and rainfall, let's say up to n years. So every 1st of July you have the amount with you, and you have data for n years. So if you look at the temperature time series, it will have typically these kind of things. On 1st of July, temperature, of course, is not a constant, it fluctuates. And then there are some record temperatures like this. Okay. Now, it turns out that for this, if you have a global warming, then of course this is not independent and identical because the mean will increase with time. But if you say if there is no global warming, then it's a good model to take to be just a Gaussian distribution of temperature around there some mean value, and assume that they are independent. And this has been studied in many different models. Okay, so this is temperature. So for temperature, IICD is a good model, roughly speaking. Okay. However, if you look at the rainfall, so again you are just monitoring the rainfall on the 1st of July, let's say in a particular city like here in Pisa, and you are observing this xi versus n. So the difference with this temperature record is that in this time series of rainfall, you can have some years where there is absolutely no rainfall on the 1st of July. So these are shown by these black dots, right? It's a totally dry day. And the blue are the wet days, meaning there is some finite amount of rainfall. So if I want to know the statistics of records in this rainfall time series, I have to take into account the presence of these dry days, okay, or dry years, if you like. Okay, and these are like the in physics language, these are like the random point disorders in an otherwise IICD sequence. Okay, so you just there are some point disorders which is there, and because the point is that the record, now if you look at the records, a record cannot happen on a dry day, right? You have to have finite amount of precipitation in order to see records. So somehow the dry days here are like disorders where the records cannot happen, okay? And this is the sort of thing that we wanted to analyze, that what happens to the record statistics in presence of such point disorders. Okay, so what is the sort of simplistic model for this? So you say that, okay, the simplest model is what is called the Bernoulli model, which says that a year, so I have this time series, and you say that a year is dry with probability PQ and wet with probability P, complementary probability. Okay, so it's like a binomial variable. And so on the dry years, of course, there is no precipitation, so xi is exactly 0. And in the wet years, you have a finite precipitation where xi is positive. Okay, and this finite precipitation, of course, it can be random, and you take from some underlying distribution P of x. Okay, so Pw of x is, I assume that it's a continuous distribution and supported over a finite interval, and eventually I'll take the delta going to 0 limit, but over this interval. And so you draw the wet years from this distribution, and the dry years are just points, they are 0 essentially. Okay, but the wet year can happen with probability P, and once it happens with probability P, then you draw the actual amount of rainfall from some underlying distribution Pw of x. Okay, and we want to know what is the the key point is that the record can happen, and this is where the correlation comes from. The record can happen only on a wet year; it cannot happen on a dry year. Okay, so the dry years are like blocks, which your records cannot be counted on these guys. So as I said, they are like point disorders in the IICD sequence. So how do we analyze this model? So this is the model. This is the model we want to study. And it turns out it's a pretty realistic model of records for rainfalls. So to study this model, so first thing you realize that this is universal, and for a very simple reason. And the reason is the following. So if I have this rainfall time series, so as I said, a record can occur only on a wet day. So the point is that the relevant number of entries in this time series is therefore the number of wet days, right? Which I call NW. So I take a time series of step n, and I look at how many days are wet, and that's NW, which itself is a random variable, of course. And this random variable has a binomial distribution. If I have a total number of entries n, how many days are wet? So the probability that you have n wet days is just a binomial distribution with this parameter p, or q if you like, probability of dry day. So this we know already. And the rest of the guys where the record occurs, they just form an IICD sequence, right, with a distribution drawn from Pwx. Therefore, if I know the record statistics for the IICD sequence, but the only thing that happens is that the number of entries in this previous calculation, it just becomes a random variable drawn from this binomial distribution, and you have to sum over all possible NW. So this is going to be the P of Rn, okay, in this Bernoulli model, in presence of record, dry days. So the thing is that immediately you see that because this guy is universal, So this is going to be universal. It does not depend on the distribution of the rainfall on the wet day. Okay? So this is very easy to see that it's universal, and you can actually do some computation with this formula here. But this formula hides somehow one fact, which is that you want to know how the presence of these point disorders or dry days is actually affecting the occurrence of record process, okay, in time. So I want to look at how, if I have these point disorders, how does it affect the sigma variables, basically, record occurrence process in time. Okay, this somehow hides that fact. It gives you a global thing. I want to observe something on a local scale as a function of time. Okay, so for that we actually decided to look at it in a slightly different way. And so what happens here in presence of the dry days, you can think of this like an IICD sequence almost, except that it's no longer IICD but IID, in the sense that this is not continuous distribution anymore. It has an effective delta function at x equal to 0. These are the dry days, right? So there are two parts to it. Okay, and so then again you do the same exercise. You say, okay, RK is the record probability that a record happens at ERK. So how do I calculate that? So for the record to occur, so this guy must be a wet day, which happens with probability 1 minus q, and then its value is taken from this PW of xk, and all the previous guys should be less than xk, and they are drawn from this effective distribution P of x. Okay, and again if you make this change of variable, all that changes from previous cases is just the record rate just becomes 1 minus q to the power k over k. Okay, so again when q equal to 0, you get back the previous result 1 over k, but now we have this additional factor which comes from these point disorders induced by this delta function here. Okay, but once again it's universal, and consequently you can calculate the average number of records, and it goes like 1 minus q to the power k by k. It's universal for all n, and for large n in particular it goes like log of p, and this p is 1 minus q plus some constant which is the Euler constant. Okay, so average number of records is very nice. You can compute exactly. What about the correlation? And this is the interesting part. So again I can compute the correlation. What's the correlation between sigma k and sigma j? Probability that a record happens at step k and step j. Okay, so once again if you do the same calculation, I'm not showing you, again you can make it to map it to uniform distribution, and right, all that happens is the lower limits instead of 0, they are now depends on q, and as a result what you see is that this is no longer same as average sigma k and sigma j, and which means that somehow these point disorders induce correlations between these record occurrence events. Okay, and you can calculate this correlation function exactly, this 2-point connected correlation function, and it turns out to be this is negative. That is, there's an anti-correlation. If there is a record happens at step k, there is a less probability of record happening afterwards, and so they are anti-correlated, and moreover it actually decays as a power law. If you fix k and increase j and ask how does the correlation function decay as the distance j minus k, it goes like 1 over j minus k square. So it's a power law correlated 1 over j minus k. So it's there, the sigma k's, they get very non-trivially correlated just due to the presence of q, these disorders. Okay, if q is 0, they are all 0. Okay, so you see that it's just a very simple change, but it actually induces a non-trivial correlation between the sigma events, and so as a result you can calculate the variance. So it's going to be highly non-trivial, and okay, I'm not showing you the calculation, you can compute it for all n, but in the large n limit, variance again goes like log of Pn. So all that changes from previous cases is that the p just comes in here plus some extra constant, and now so the variance is actually pretty complicated expression. So what we wanted to study the somewhat simpler limit, and the simpler limit is what is called the random record limit, which is that when you take the n goes to infinity, but this probability of dry day p goes to 0 limit, but keeping this product t is like a time if you like, which is n times p fixed. Okay, so in that case the formulas simplify and you can obtain more explicit results. So for the moment I'll just study this random record limit. So if you calculate the mean, which of course you have an exact formula for all n, but you take the scaling limit and you see that it's just a function of just this time np, and this scaling function mu t is just given explicit expression, this guy. Okay? It behaves like linear for small t, and it goes like log t as large T. Okay. Similarly, the variance you can compute, and again in the scaling limit it becomes a single function of this time variable, effective time variable, which is n times p, And this function v of t, again, is a universal function, and it's given by, if you know this mean mu t, is just given by explicitly by this formula. So then we said, okay, so how about the Fano factor? So we wanted to calculate the Fano factor just to see, because in this case they are correlated sigmas. So we wanted to see what happens to this Fano factor. And you can calculate the Fano factor explicitly again given by the explicit formula. And it behaves like 1 minus t over 2 as t goes to 0. So it goes to 1 as t goes to 0. And it also goes to 1 as t goes to infinity as a very slow pi square over 6 log t. So if you plot, it looks like this. So Fano factor as a function of time means this Pn. Okay. So it actually has a non-monotonic behavior. It starts at 1, then goes down, and then it goes up, and eventually at very, very long time, it approaches again back 1, okay, but very, very slowly. But the point is, you recall that in the IID case, IICD case, we have seen that the Fano factor is a continuously monotonically increasing function of n. But here, it's a non-monotonic function. It first goes down and then goes up. Okay, so and this happens because of the correlations, anti-correlations. Okay, so these correlations between these sigma events, it makes it and in fact, the fact that it's non-monotonic is a sort of unique signature that the underlying record occurrence process is completely correlated. Okay, and so we saw this. So we were very, it was very nice to see this calculation, and this is nice. This is for different t, and this is the scaling function. This limiting function is this black line. So we wanted to see if this is, how does the real data actually match with this. So we looked at this data from the Cologne station over 1975 to 2010. And so this blue boxes here are the data for the Fano factor obtained from the real data, and this red line is this Brownian model or prediction basically. And you see it actually matches reasonably well. There is a little bit variation here, which is okay. But this is a very simplistic model, but at least qualitatively it works very well. Even quantitatively, I would say. Okay. So then you can ask, okay, what about the full distribution of the record number? And the point is that in this Bernoulli model, you see this variable sigma case, they are strongly correlated. So therefore, unlike in the IICD case, you can no longer write a simple master equation like this, because the RNs are strongly correlated in time. Okay, so you cannot write this. Okay, so to solve this is not so easy, I would say, because it's essentially non-Markovian process. Because of this correlations in sigmas. But okay, I'll not go into the details. But what we managed to do is to calculate the full generating function of this probability distribution of R of n, lambda to the power r and z to the power n. And it turns out it has a very, very simple expression. It's like this. And we used a sort of renewal approach to compute this. And again, of course, you can see, as you would expect, of course, it depends only on this parameter q, but totally independent of the underlying distribution for the weight days. And in particular, as n goes to infinity, again, this converges to a Poisson distribution, but all that changes is that log n just gets renormalized by Pn. Okay? So P is the probability of a weight day. And so you can actually write down this distribution in a large deviation form, which is somewhat unusual, because you see that this is just Poisson distribution, but if you write down in a sort of large deviation form, then it has a non-trivial large deviation function 1 minus x plus x log x. But the point is that it's a very unusual large deviation form, because usually in statistical mechanics you have probability distribution of a random variable is like extensive in time, so it's e to the power minus t into some function of r over t. But what happens here, it's not this t is actually like the log of the p of n. Okay, so it's not really n here, but log of n. And this type of sort of anomalous large deviation form, we actually noticed it before in in other problems, completely different problems. For example, one of the problems is the number of real roots of a random polynomial. So this was some work that we did with Gregory, and he has done more recent work with Micha Poplowski. And also in the distribution of entanglement entropy in random quantum spin chains, there's some recent work with David Hughes and Tritev Devakul. So there, we have seen this kind of unusual large deviation form. And so it was nice to see that it appears in this simple model, Bernoulli model of record rainfall, the exactly similar large deviation form. Okay, so this large deviation form, of course, has a quadratic minimum. And so if you go to the minimum and analyze the quadratic form there, you get back a Gaussian distribution. So interesting thing is that, so the central limit theorem holds even though the sigmas are power law anti-correlated. Okay, so they decay like 1 over j minus k squared, so they are strongly correlated, but still the central limit theorem holds. That is, the distribution, typical fluctuations around the minimum are actually, or maximum if you like, of these distribution are Gaussian. Okay, so let me just summarize now. So essentially what we studied in the last part, I mean apart from the review in the beginning, is that the simple and very realistic Bernoulli model for rainfall records. It's exactly solvable as I showed you, and also it's universal for all n. That is, it does not depend on the underlying distribution of the rainfall wait days, actual rainfall distribution. And the main key finding that we have in this work is that the presence of dry years, okay, with probability q, it induces a long-range anti-correlations between the record-breaking events. Okay, and as a consequence, what you have a pronounced minimum in the Fano factor, which we saw that it matches pretty well with the experimental data, and also therefore it provides a distribution-free null model for precipitation time series. When you are looking for these daily rainfall records on a given calendar day over a sequence of years, you can take it as a distribution-free null model, because I don't need to know what is the distribution of PWX. I mean, if you see that it is like this, then you can say that the Bernoulli model is a pretty good model. This is the sort of null model. Okay. And okay, I didn't have time to talk about the records for random walks and levy flights. I know many people here are interested in random walks and levy flights, but since I don't have time, I can just refer to our recent review with Claude and Gregory, which has a lot of discussion on random walks and levy flights for the records. Okay, thank you very much for your attention.
Okay, thank you very much. We have time for questions. Yes, David.
If you take some correlations between the dry years, yes. So in fact, I mean, what we studied, no, you're right. So I mean, what we studied in a more general case, imagine that you take the dry years from some, some in dry interval from some interval, and then the weight from another interval. Even that model you can actually solve. Yes. So that's a special case of that is this Bernoulli model, basically, right? But it's a bit more complicated. This.
Yes, Denis? I don't know. The microphone doesn't seem to work. Yes, it does.
At the end of the first part of your talk, you said that this universal character of statistics can be used as a null efficient distribution-free test for null hypothesis of independence.
Yes.
How efficient it is as compared to other conventional statistical tests?
I don't know. I mean, the conventional, most commonly used is the Kolmogorov-Smirnov test, basically, which says that essentially it will be a Brownian bridge if you look at the maximum of this guy. Okay, but this one is also used. I mean, especially in climates. This has most people use record statistics as a sort of null hypothesis. These things, but probably it's easier there. I mean, because for whatever reasons. I mean, but I don't think I mean, I don't know if anybody has done a comparative studies of which one is better or something. So.
So if you broaden the delta function a bit, then the correlations would immediately go away. Is that right?
Well, I mean, yeah, even the
delta function peak.
Yes, right. No, I mean, then it becomes a continuous distribution.
Then
yes,
it
right, exactly. Yeah. You need a delta function, really. I mean, so which comes naturally here. I mean, in some sense.
But if you put a delta function anywhere,
if you put a delta function anywhere, then also it will be different. Surely, yeah, sure, yeah.
When you construct the weather data for 1st of July, you do it in some location. You do it on some location on Earth, I understand.
Yes.
And then to create an ensemble, you have different locations?
That's right. No, different. No, it's the same location, but it's different years, right? I mean, different.
But what is your...
You can say. Yeah.
So first of all, you can do it for every calendar day, right? So you have 300 for one location.
Yeah, but then you are comparing members of their ensemble, which are totally different. You're comparing the 1st of July to the 1st of January?
You see, the point is you'll have some different distribution on different days, but that doesn't really matter. 5 days, and then we screen this ensemble in such a way that we only pick stations where the average rainfall probability was about 1/2, which is sort of the global average. So if you look all over Germany, on average, 50% of the days have
Yeah, but then your different stations in Germany are strongly correlated.
No, of course, yeah, sure.
So this is why, in some sense, it's surprisingly, I mean, it fits surprisingly well, I would say.
Gleb, I think Gleb had a question. Yeah.
Oh yes, I have. Just I'm curious because you took a Fanny factor which is dimensional.
Yes.
And if you take something like coefficient of variation, so you will take standard deviation over the mean,
Right.
will it be still non-monotonic? Or they compensate?
Fanny factor, you can prove explicitly that it is non-mono. It's a sufficient condition that if it is non-monotonic, it's a sufficient condition to show that underlying variables are uncorrelated. In other words, if the variables are uncorrelated, you can prove that the Fanny factor would be a monotonically increasing function of n. Okay.
Yeah, but the coefficient of variation, will it be non-monotonic as well, or?
I don't know.
They will compensate each other.
Maybe they might compensate for each. I mean, the Fanny factor has this property that it's always a monotonically increasing function of n.
Okay.
Yeah.
Okay. Thank you.
Do you have an idea of the typical configurations that eventually produces these algebraic anti-correlations?
Typical.
What causes these algebraic anti-correlations? I mean,
It's very hard to. This is a question. We try to spend quite some time to have an intuitive feeling of what causes these power law correlations. I mean, at least we don't have. I mean, honestly, we don't have. I mean, what we have is you compute and you see that it happening. But what causes this? I mean, okay, after calculation you can always cook up reasons, but it's not completely clear. No, q to the k is just you fix k and you see as a function of j minus k basically. Okay, for a fixed k, if you ask how does it depend on the difference of time between the two events, that decays like a power law 1 over j minus k square.
Yeah. Technical question. I mean, the dry days are very important according to what you're saying, but the definition of dry day is a bit arbitrary. So there can be a very small range. What I'm trying to say is that if you exclude a very tiny range and just attribute them to dry days, the results will probably remain the same.
It will remain the same. I mean, it's just the only thing is that you have basically part of the spectrum, this p of x, which is continuous, and then there's a delta function as long as you have
and it doesn't matter where exactly you put it. Yeah. Thanks.
Okay. Thank you very much.
Okay, thank you very much, Gregory, and thank you, Gregory and David, for getting us together here. So since this is a meeting about probabilistic methods and extreme value statistics in cell biology, I thought it would be appropriate to tell you a little bit about our recent work on fitness landscapes and adaptive walks. So these are stochastic processes that occur in genetic space. And, but you'll see that there are some connections even to the topic of record statistics that Satya was talking about before. And of course, these adaptive walks are essentially trajectories in genome space that populations trace out during evolution. And understanding those is very important for the topic of understanding the predictability of evolution, which is a topic of our recently approved new collaborative research center in Cologne. And so the sort of second part of the talk about adaptive walks in correlated fitness landscapes is joint work with Suchan Park in Seoul, Johannes Neidhardt, who was a student, and Ivan Schendro, who was a postdoc with me in Cologne. So the concept of fitness landscapes was introduced by Sewell Wright in the 1930s. And these are two figures from his original paper. So the idea is that you represent genetic changes as a graph. At that time, of course, the structure of DNA wasn't really known, but it was known that genes were arranged in a kind of linear way. And so you could think about what happened to a genetic type. So this is the original type, the so-called wild type. And then there can be a genetic change at a gene A and another one at a gene B. And then you can have the combination of the two. And you can sort of extend this to 3 genes, 4 genes, and so on. And you get these sort of genotype graphs. And so the idea that Wright was pursuing was to assign fitness values to each of the nodes in this graph. So each genotype gets a fitness value, which is a measure of reproductive success, something like the average number of offspring that an organism leaves. And then you can think about evolution as a kind of hill climbing process in this fitness landscape. And to sort of visualize this hill climbing process, he also put the second picture where the genome space, or the genotype space now is a plane, and you have a kind of topographic map, and you have these peaks that the populations will try to climb. But of course, there's a big difference between this graph, which is technically speaking a high-dimensional hypercube, and this two-dimensional plane. And this is something that has caused a lot of confusion in evolutionary theory over the years, which Wright already was very much aware of. So let me try to define things a bit more precisely. So we're thinking about genotypes. These are sequences of things that I call loci. So these could be individual genes. These could be nucleotide sites in a string of DNA. It doesn't really matter. The main point is that at each of these loci, we have a binary variable, which can be 0 or 1. So if there is no mutation, so if we have the sort of wild type, we have a 0. If there is a mutation, you have a 1. And a fitness landscape is then simply a function on the space. Okay? And if you endow this space with a natural distance, a so-called Hamming distance, where you just count the number of differences between two sequences, this becomes a hypercube. Now, there are some technical biological terms that actually will not play a big role later in the talk, but I thought I should mention them. There is a notion of epistasis, which means that there are interactions between the effects of different mutations. So this just means that if you change a 0 into a 1 at one site, the effect of that on fitness will depend on the states of the other loci. And there's a particularly important kind of epistasis, which is called sign epistasis, which means that a mutation at a certain locus can be beneficial, increasing fitness, or deleterious, decreasing fitness, depending on the state of other loci. And how that affects the fitness landscape is illustrated here. So this is the simplest case to visualize, where we just have two sites. So we have 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. And here we can draw fitness as a kind of function on that. If there are no interactions, then this fitness function just defines a kind of plane, which means that changing a 0 to a 1 on the first site has the same effect here and here, independent of what the other side does. If you have interactions, then this thing gets distorted. And in particular, if you have sign epistasis, then you see that this little fitness landscape now has 2 peaks, which means that the changing a 0 into the 1 along this edge decreases fitness, but doing the same along this edge actually increases fitness, right? So this is how sign epistasis gives rise to rugged fitness landscapes. And so the notion of ruggedness is the same as you would have intuitively. A rugged landscape is a landscape with many peaks. And what Wright was worried about was the difficulty of navigating, for evolution of navigating such a rugged fitness landscape. There's a theorem that says that you need reciprocal sign epistasis, which means that you need to have a pair of loci where the sign of the effect of one locus depends on the state of the other in order to have multiple peaks. So that's sort of the paradigmatic picture of a rugged fitness landscape over 2 loci. So this is sort of the general framework that I want to think about here, and what I want to do in this talk specifically. So I want to begin by giving you a kind of overview of what is known about real fitness landscapes, because the reason why this topic has sort of picked up a lot of speed over the last 10 or 15 years is that we are now getting data on real fitness landscapes. We'll then think about how evolution proceeds to navigate these rugged fitness landscapes. This is the topic of adaptive walks. And in particular, since this is a meeting about extreme events, I want to tell you a little bit about how extreme value theory is being used in this context, which actually is not something that statistical physicists invented, but there's a kind of school of thought in evolutionary theory that makes use of extreme value theory. So let me begin with showing you some empirical fitness landscapes. This is, of course, not an empirical fitness landscape, but I think it's a nice picture. And this is basically based on 2 review articles, one sort of more biologically oriented, and another one that we published in JSTAT a couple of years ago that shows more examples than I have time to describe to you here. So the work that really got this started appeared in 2006 by Dan Weinreich and collaborators. And what they were thinking about was how antibiotic resistance can evolve. So they studied a model system, which I will get back to a little bit later, a certain enzyme which is called beta-lactamase. And this is an enzyme that cleaves a certain class of antibiotics, named the beta-lactams, such as ampicillin, or this is a kind of second generation beta-lactam, which is called cefotaxime. And so what Weinreich was interested in was to see how highly resistant variants of this enzyme could evolve. And so there's a wild type here. So the notation here is that the wild type has all minuses and the evolved type has all pluses. So there are 5 mutations involved here. And so what he did was to generate all the intermediate states. So if you have 5 possible mutations, you have 2 to the 5 or 32 different genotypes, and you can make all these enzymes and you can just test their ability to cleave the antibiotic, and that gives you a number here, which is a measure of resistance, the concentration of antibiotic that the bacteria can tolerate. And the main discovery here was that there are not that many pathways along which this enzyme can evolve. So the pathways along which it can evolve are those along which resistance increases monotonically. Okay? And there are 120 possible pathways because there are 5 mutations, so 5 factorial is a 120, and out of those only 18 were found to be evolutionarily accessible, and this was interpreted as saying that this evolutionary process is rather predictable because there are not that many routes that can be taken. So this was sort of the first, or one of the very first examples of a small empirical fitness landscape of 32 genotypes. Since then, of course, things have sort of been scaled up. So this is an example. This is a fitness landscape that we have worked with quite a bit for a certain fungus. This contains 8 mutations, all of which are individually deleterious. So this is a different visualization. There's always an issue of how to visualize these things, but here I'm sort of plotting fitness as a function of the number of mutations. So for each if I have k mutations, I have L over k different genotypes, and these are the fitness values of these different genotypes. Some of them are lethal, so some of them have fitness 0. In particular, if all these mutations are present simultaneously, the fungus is not viable anymore. But you have a lot of variability, and these red points are all local maxima. So these red points all correspond to genotypes where all the possible addition or removal of a mutation decreases fitness. And this is a recent example from the group of Kondrashov, which is a very big data set now. This is a segment of a certain gene in yeast. And so these now contain hundreds of thousands of nucleotide sequences. But you can sort of see a similar overall structure in the sense that there are, so this is fitness, this is sort of the wild type fitness. You have a couple of variants that are actually better. The vast majority, of course, are worse, and many of them are lethal. And this is, of course, what you would expect, and this is something that I will come back to later in the talk, that generally you expect random mutations, of course, to make things worse, right? So you don't expect random mutations to be able to improve function, at least not in most cases. So this is sort of what we have. So we have an increasing amount of data on these kinds of fitness landscapes, and now we want to think about what that means for the ability of evolution to navigate these landscapes. And here we can get back to Sewell Wright.
Also data which tracks the system actually takes when it's left alone?
Yes, I mean, so in particular, and I'll get back to that. I mean, for this antibiotic resistance enzyme, there are also in vivo experiments where people sort of try to follow the path that are taken. And I'll get back to that. Yes, to some extent this is possible. And of course what one often discovers, especially with small data sets like these, is that the path that you have mapped out is not the one that is being taken because there are other paths that you don't see. I mean, there's always an issue, you know, with these spaces being so large that it's hard to sort of map them out completely. But I'll get back to that. So Sewell Wright, as I said, he was sort of thinking about the problem of navigating such landscapes. So in a landscape like this, he says, selection will easily carry the species to the nearest peak, but there will be innumerable other peaks that will be higher, but which are separated by valleys. And so this is sort of what makes this a complicated problem. Now, there are different ways of trying to quantify what one could call evolutionary accessibility. One theme that we have also worked on quite a bit is to make a model for the landscape and then quantify things like the number of local peaks or the number of fitness monotonic pathways. So this is a kind of static analysis. You just take your landscape and you try to figure out how rugged it is. However, this is not the most important question, maybe, because even if uphill pathways exist, it's not clear if populations can really find them. So this is like, you know, if you're hiking in the mountains and if it's foggy, then even if there is a nice path to the peak that you want to take, if you don't have a map and if you don't see it, you will not be able to find it. So the point of view that I want to take in this talk is a kind of more dynamic viewpoint. And so we're looking at populations that are trying to navigate such a fitness landscape to something that is called an adaptive walk with local rules. So I'll tell you next what that means. So we have to define a kind of dynamics on these fitness landscapes. And the dynamics that we're using in this field goes under the name of strong selection, weak mutation. It's essentially, if you think about this in terms of statistical physics, of course you can think about the whole thing as a kind of spin model. And then this would be something like low temperature spin flip dynamics. So weak mutation, first of all, means that these mutations are rather rare. So most of the time, the population is just sitting somewhere in this space of genotypes. Once in a while, a mutation comes up. So one individual has a mutation, and then no further mutation comes. So that means that under this population dynamics, either this mutation will be able to spread. This is then what we call the process of fixation. So if it fixes, it means that after a while, the whole population has that mutation, or it goes extinct. Okay, so essentially, you have a mutation arriving, and then if there is a fixation event, it means that the whole population moves over to another site in this fitness graph, or it is lost, so nothing happens. So that's like an attempt in a metropolis algorithm, say. And whether or not a mutation succeeds depends on its selective advantage. And so there's a famous formula due to Komura, which says that the fixation probability, so the probability that a mutation goes to fixation, depends on its selective advantage. So the fitness difference compared to the original type, according to this formula. This is actually a kind of first passage problem, if you will. I mean, you just have to solve the probability that the population reaches the state where everybody has a mutation rather than reaching the state where it's going extinct. So this is the fixation probability. And strong selection means that if S is negative, then you see that this term becomes very big. And so if S is negative, then basically this probability is 0. And if it's positive, that is, if the mutation is better, then we can neglect this denominator, and we get something like 1 minus e to the minus 2s. And if s is also small, as it typically will be, this is essentially 2s. So this is then called this is a result due to Haldane from the 1920s, that the probability of fixation of a mutation is simply proportional to its selective advantage. Now, if you assume that these conditions are met, and these are certain conditions on the mutation rate, the population size, and so on, then the dynamics is rather simple. Then the population will just be moving uphill in this sequence space until it finds a local maximum, and there, at least on this time scale, it will stop, right? Because there will be no further positive mutations available. And so formally, this is a Markov chain, with transition probabilities given by this function, this Markov chain is absorbed at a local maximum in the sense that there the process stops. Okay, so this is sort of what we call an adaptive walk. Is this clear so far? Okay. Okay, so now let's try to get some results and also see where extreme value statistics come in. And I'm going to start with simplest case of just a single step. Okay, so a single step of evolution means that your population is sitting at some point in this genotype space, a mutation comes along, and now this mutation either fixes or not. And this problem was posed first by Alan Orr, who's done a lot of sort of fundamental work in this area in the context of asking for the predictability of evolution. So this paper is called The Probability of Parallel Evolution. So we consider the following setting. Suppose we have a certain number of beneficial mutations that are available. Okay, so we're sitting, our starting genotype is here, and then we have a certain number of other genotypes that we can reach, and they all have higher fitness. Okay, so we have an ensemble of mutations that can occur. And these have fitnesses Fi, which are larger than the wild type fitness, so their selection coefficients are Fi minus F0. And so what we're asking is, what is the probability, if I do this experiment twice, what is the probability that the same mutation will fix in both populations? This is what he calls the probability of parallel evolution. Now the probability that the ith mutant will be the first one to fix, and this is something you can do a formula calculation, but I think it's fairly obvious that this will just be, if the fixation probability is proportional to S, then this relative probability of the ith mutation to fix rather than some other mutation is just its selective advantage divided by the selective advantages of all the other ones. Okay? And so the probability that the same mutation is fixed twice is just the sum over pi squared. So this is something somewhat similar to an entropy. This sort of quantifies how different these PIs are. If the PIs are all the same, this will be 1 over n. And if one of the PIs is much bigger than the others, then it will be 1. Okay? Now, of course, what this will be will depend on the statistics of the Fi. Right? So this is the problem. And the statistics of the Fi, of course, generally we don't know because there is some complicated biology behind it and so on. But this is where extreme value theory comes in. So let me just, I guess most of you know this, but let me just review this for you, this classical extreme value theory, which states that, yeah.
When this guy moves to a new fitness, so you're assuming that the fitness landscape doesn't get affected by the motion of this guy, right?
No, the fitness landscape doesn't get affected. No, this is just given. Yeah. So extreme value theory tells you that if you look into the tail of a probability distribution up to some rescaling, the tails are always of this generalized Pareto form, and there is the so-called extreme value theory index, kappa, and there are these 3 classes. If it's positive, then the tail is power law-like. If it's negative, then the tail is truncated. This is called the Weibull class. And if kappa is equal to 0, we're in the Gumbel class, which is sort of contains distributions that decay faster than power laws. And so the idea now, and this goes back to Gillespie, but has been elaborated on by Orr, is the following argument. So obviously this distribution of fitness values of random mutations is something very complicated that we don't know. What we do know, however, is that when an organism is viable, it's already very well adapted to its environment. So whatever the distribution is, the fitness of mutations that makes the organism even better adapted must be in the extreme tail of the distribution. Okay? And if it's in the extreme tail, even if the distribution is unknown, we know that it has to take one of these shapes. Okay? So that's sort of the idea of Gillespie. And this we can now apply to this problem. Right? So we can now apply this to this problem of computing the probability of parallel evolution. And what Orr did in his paper in 2005 was to calculate this thing for the Gumbel class. And this is a calculation that is not entirely trivial, but it leads to a nice simple result, which says that this P2 is 2 over n plus 1. So if the neutral expectation, so if there was no selection and all the mutations were equivalent, you would have 1 over n. So it gets a little bit bigger. Okay? And that's, of course, what you expect. If there's selection, then the probability of seeing the same result twice will be increased. And here it's increased by a factor of 2. Subsequently, Joyce and collaborators extended this to other generalized Pareto distributions, and they did the following calculation. So you want to calculate this thing. First you sort of approximate this average of a ratio by a ratio of averages, And then you can compute both of these for the Pareto distribution, and this is the result that you get. Not surprisingly, this of course doesn't work if the distribution doesn't have a second moment anymore. But of course, nevertheless, this calculation does have a finite answer for any distribution, just by definition. But of course, this factorization cannot work anymore. Okay? Now, to calculate this in the general case, one can use an identity for evaluating inverse powers of random variables, which is given by this formula here. And so we did this in order to calculate these general. So you can, of course, generalize this rather than just calculating P2. You can calculate this thing Pk, which is just the probability of finding the same mutation k times. And the results are the following. So the interesting case is the power law case, right? So we have this P of S decaying as a power law. When alpha is less than 1, so this corresponds to kappa being bigger than 1, then all the moments are infinite. And this is actually something that was computed by Bernard Derrida a long time ago in a different context. And then you find that all these moments are actually independent of n. So independently of how many mutations you have, you always have a fixed probability of finding the same mutation twice or k times. More interesting is the intermediate case. So when alpha is between k and 1, then the moments of order k and larger are infinite. And what you then find is that this pk, in the neutral case, this pk would go as 1 over n to the k minus 1, but now it goes as 1 over n to the alpha minus 1, which is independent of k. And in particular, these ratios are independent of n. And if alpha is greater than k, and then the moments exist, and then this factorization is asymptotically valid, and you get back to the result of Joyce. Okay, so here you see how having a heavy-tailed distribution of these fitness effects makes evolution much more predictable, because it becomes much more likely to have to see the same mutation many times. Now, this might seem like a sort of somewhat arbitrary, yeah.
Pk is just the probability of having k successive.
Of seeing out of n, seeing the same mutation k times, right? So this might seem like a sort of arbitrary academic exercise, but in fact, it turns out that this is of some relevance. So here I come back to this beta-lactamase enzyme that I mentioned before. This is what it looks like. And so with our collaborators at the University of Wageningen, we looked at this in more detail. And so they conducted a systematic search of finding mutations in this enzyme that increase resistance against cefotaxime. So it turns out there are 2,500 possible point mutations, and 48 out of those increase resistance. So this is sort of our panel of beneficial mutations. And we estimated that altogether there might be roughly 100 of those. Now, of course, the question is, what is the distribution of fitness effects? One can measure these fitness effects. And then one can, and this is a kind of histogram of fitness effects at different concentrations of antibiotics, and one can perform a maximum likelihood analysis to try to estimate whether this conforms to the extreme value hypothesis. And what we find is Fréchet behavior, at least for large concentrations of antibiotics, with a kappa around 1. So these are the estimates of the kappa values. And here is kappa equal to 1. So these are clearly heavy-tailed fitness effects. And now you can calculate the probability of parallel evolution from the empirical data. So this is now the probability of seeing the same mutation twice as a function of antibiotic concentration. And you see that as the antibiotic concentration increases, the distribution becomes more and more heavy-tailed. So the difference between the strongly resistant and the weakly resistant mutants becomes larger, and this strongly increases the probability. And so this red line is a related quantity, the probability that you see the largest of the mutations, and you see that this goes up to almost 40% at the highest concentrations. And this is what you would expect under Gumbel statistics. And this was in some sense confirmed. Now this comes back to Yarif's question. If you now do an in vivo experiment and you run replicate lines, then our collaborators found that in 10 out of 12 replicant lines, the largest effect mutation was actually substituted in the first step. So this shows at least that in a qualitative sense that there is a strong dominance of the largest fitness effects in the system. Okay, so this was the first step of adaptation. Now, of course, we want to look at adaptive walk. So now we can, we look at the pathways in these fitness landscapes consisting of several or many of these steps. And there's a big literature on this. And so people have sort of looked at various versions and simplifications of these models. What I have described to you so far and what goes back to the work of Gillespie and Orr is what we can call the true adaptive walk. So there, as I told you, the rate of going to a higher fitness type is proportional to the fitness difference. But you can sort of simplify the problem and say, okay, I just look at all the fitter genotypes and I pick one of them at random. Okay, this is what is called a random adaptive walk. It was introduced by Mackin and Perelson in '89. Another variant, again introduced by Orr, is called the greedy adaptive walk. So there you say we just go deterministically. We look at each step, what are the possible fitness values that we can see, and we always pick the biggest one. So that's like a steepest ascent optimization algorithm. And a somewhat curious modification that we studied recently, motivated by spin glass work, is called the reluctant adaptive walk. So this is the case where you always pick something that is better, but you try to improve yourself as little as possible. Okay, so this is a very shy walker that only wants to do small steps. This doesn't really have, as far as I know, any biological realization, but it's sort of an interesting problem to study mathematically. And so, as I said, these walks always terminate at some maximum. So the question of interest is the length of the walk, so the number of steps that you take until you find a maximum. And also you could, although I'm not going to talk about that, you can think about the height, that is the fitness that is actually achieved in the end. Now there's been a lot of work on this for the simplest case. Now the simplest setting would be that you just assume that the fitness values of your different genotypes are IID random variables, right? This is called, in this case, the house of cards or mutation landscape model. And then there are a number of results. So if you start at a low fitness genotype, then if you do a random adaptive walk, then the length of the walk is just log L plus a constant. So L, remind you, L is the number of dimensions. So L is the number of loci that you have. This was shown by Mackin and Perelson, but also more completely by Flyberg and Lautrup. You can do a greedy adaptive walk, reminding you again, so you always pick the highest possible value in each step. And there's a very nice little calculation due to Orr, which shows that these walks actually have finite length. So if you, in a completely uncorrelated landscape, you always pick the highest possible value. Then after, on the average, 1.7 steps, you have found a maximum. The reluctant walks, on the other hand, are very long, so they take typically on the order of L steps before finding a maximum. And all of these results are universal because they only depend on the ordering of the fitness value. So you can sort of change the distribution of fitness values very much like the record statistics that Satya talked about. These don't depend on the distribution. The true adaptive walk does depend on the distribution, but it only depends on the distribution, again, through the extreme value index. And so what we showed some time ago is that the length of the walk in this case is still logarithmic, but with a prefactor that depends on the extreme value index. And when kappa becomes equal to 1, so this is a case where the distribution doesn't have a mean anymore, the length becomes of order 1. So if you have very heavy tail distributions, again, you basically need of order 1 steps to find a maximum. And if your initial fitness is not very low, then you just have to sort of rescale L by this fitness, because that means that in your initial state, you already have a reduction of the number of directions in which you can go. Okay, so what I want to discuss in the last 10 minutes is more recent work on correlated fitness landscapes. So all of this was about uncorrelated fitness landscapes. This is nice, but this is presumably not very realistic. So if you look at empirical data, it's pretty clear that real fitness landscapes are not uncorrelated. They have correlations. They're sort of intermediate between something that is maximally rugged and something that is smooth. So one model that accounts for this is called the Rough-Mount-Fuji model. So here, this is the definition of the fitness landscape. So sigma is, again, my binary sequence. And this now has two components. There's an IID component here. But then there's another component here. So d of sigma, sigma 0 is the Hamming distance between the sequence and the reference sequence. So the reference sequence is sort of at the bottom of the hill, if you will. And c is positive. So this means that as you, c is, yes. So as you go away from the reference sequence, your fitness increases deterministically by c, but there's also a random component. Okay, so if you go to the antipodal sequence of the reference sequence, your fitness would be maximal. Okay, so you sort of move uphill, but there are some fluctuations on top of that. And so depending on what the relation is between c and the standard deviation of the distribution of the etas, you can sort of tune the ruggedness of this landscape. And so what was shown by Hegarty and Martinson is that if you just ask for the existence of fitness monotonic paths, so you just want to know, is there a path from where I start to the peak? This is always guaranteed as long as c is positive, right? So c sort of helps you finding the peak because it's a kind of deterministic gradient. And so what we were interested in was to look at adaptive walks under this scenario. And so the question is, how big does this gradient have to be to allow an adaptive walk to actually find the peak? And this is, so this is just an illustration, and we're sort of going to work in a kind of tree approximation. So this is our initial point, and these are now the distances, right? This is the reference sequence, distance 1, distance 2, distance 3, and so on. So at every point, I have a certain number of neighbors. Some of them are better, so these are the ones with arrows. Some of them are worse, so they don't have arrows. So I can go under a random adaptive walk, I can go to one of these arrows. So I might pick this one. And then I have a new neighborhood. And in this new neighborhood, I'm seeing a new set of random variables, but they are all increased by 1. Okay? And so this way, I trace out this path until I end up at a point where all the neighbors that I can still access are worse. Okay? And this is where the walk will stop. Now, for this, you can write down a formula or a recursion relation for the joint probability that the walk takes at least L steps and reaches a genotype with a random fitness component y. And this is given by this expression here. So here is now so small p is a distribution from which I draw my fitness effects, and capital P is a cumulative distribution. And now what you can observe is that if you take L to infinity, so if you take your genotype space to be very large, then this term will vanish. And then you can convince yourself that this is actually a recursion relation that is known from the theory of records. And so this comes back to Satya's talk, except that there's a kind of modification in the sense that here there is a shift. So this is actually a record process. But here the condition for having a record is not that yk plus 1 is greater than yk, but that it's greater than yk minus c. Okay, so this is like a record process where you have a kind of increasing, you sort of help the occurrence of records along by making the condition somewhat weaker than it would be otherwise, as long as c is positive. And this is actually known in the literature as a so-called delta exceedance record process, where typically people consider the case where this is positive, so delta is equal to minus c. So this has essentially, so as you move along the walk, the values, the fitness values that you encounter are record values in this sense. And so what we found in the analysis is that, again, so this is, because you have the C, you sort of lose the complete universality, right? Without the C, we know, as Satya told you, everything would be universal. But because of the C, the structure of the underlying distribution actually matters. And it matters, again, in a kind of extreme value sense. So in particular, if the random variables are exponentially distributed, you can find an exact solution to this recursion relation. And this is what it looks like. And this solution shows that there is a phase transition at c equal to 1. Okay, so c equal to 1, I mean, exponential random variables with mean 1. So c equal to 1 means c is equal to the mean of the exponential random variable. And so here you have a phase transition between a phase where these record values increase linearly. This is sort of what you would expect, right? For c equal to 0, you know under exponential distributions that the record values increase at rate 1. So each record value is on average 1 bigger than the previous one. When c is less than 1, this is still the case, but the increment is reduced. But when c is greater than 1, the record values actually don't increase anymore. And the record process becomes stationary. And in between, there's a kind of critical phase where these record values grow as square root of L. And in terms of the walk length, this translates into the following results. So when c is less than 1, the walk length is still logarithmic, as it would be with c equal to 0. When c is greater than 1, the walk length is of order L. So this means that your fitness gradient is so large that your walk essentially traverses the entire fitness landscape and goes all the way to the end. And then there's a critical case where the walk length is not log L, but log L squared. And this is shown here in comparison with simulation. So this is the walk length versus log L in a double logarithmic plot. This is the log L squared. This is the log L that you see for c less than 1. And this will eventually cross over to a linear behavior, which sort of looks exponential in this plot. Okay, so this is what happens for a particular case of distributions. Now, in general, you cannot solve this exactly, but you can still look at a recursion relation for the mean record value, which looks like this. And this h is this combination of functions, which is called the hazard function. And this you can evaluate approximately. If you assume that this q is well concentrated, you can just replace this by the average. And then what you then basically find is that the exponential case is the only one that has a phase transition. As soon as the distribution has a tail that is thinner than exponential, then you basically go back to the case where the walk becomes of order L. And if it's fatter than exponential, then it just looks like the standard process. So the exponential distribution is a borderline case, and it's the only one that has this particular critical behavior. And this, of course, a special role of the exponential distribution here reflects the fact that the spacing between subsequent record values is asymptotically constant. And for any other distribution, it will typically either increase or decrease. Now, the last thing I wanted to mention is some results on greedy adaptive walks. So you can also look at greedy adaptive walks where you pick the largest fitness value in each step. There it turns out that there's, again, an exactly solvable case if you pick your random fitness components from a Gumbel distribution. And it has this rather amusing form. So there's a probability that the length is greater than L. And in the IID case, this would be 1 over L factorial. This is something that Orr showed. And here it becomes the Q 1 over the Q factorial, where Q is equal to e to the minus c. Okay? And correspondingly, the mean walk length is then given by what is called the Q exponential minus 1. So again, for c going to 0, this goes back to Orr's result e minus 1. But in general, this will actually be an exponentially increasing function of c. But again, the exponential, for non-exponential tails, you only have sort of two rather trivial limits. That is, either the walk length is L or it's e minus 1. And this shows the walk lengths as a function of c. So these are the full results. And you see that you have a rather good upper bound, which is just 1 plus e to the c, which is this one. OK, so with that, let me finish. This concept of fitness landscapes is an old one, but it has recently become accessible to empirical exploration. The general role of mathematical analysis, as I see it in this field, is that these mathematical models can help us to extrapolate from the low dimensionality of the empirical data to the very high dimensionality that is of relevance for genome-wide processes, which, of course, we will never be able to explore empirically. I've introduced these different walk types and emphasized that some of them display phase transition like phenomena that are governed by the tail properties of the fitness distribution. And overall, I hope I've shown you that even classical extreme value theory can provide a useful conceptual framework for the analysis of data in this field. So thank you very much.
Okay, thank you very much, Joachim. We have time for questions. Martin?
Okay, I've got a couple of questions. One, just a quick one. What was the true adaptive walk? I missed the definition.
So the true adaptive walk is just the one where the probability of going to the new genotype is proportional to the fitness difference. Okay, so it depends. So fitness difference is always positive, and the probability of picking one particular site is proportional to the fitness difference.
Right. So the other bigger question is, what about phenotypes? This is just genotype, right?
Right. Yes. So what should I?
Is there a simple way of introducing phenotype into these kind of models?
Well, the way I think about it, and if you remember my talk in Krakow at MICO, there was sort of more about phenotypes there. So the way, one way in which I think about phenotypes is, of course, that phenotypes are in the end what to some extent defines the structure of the fitness landscape. So in reality, here, throughout this talk, I've assumed that I have the genotypes and I can map them to fitness. In fact, of course, in between there is the whole organism, and there are phenotypic properties that define the interaction of the organism with its environment. So the phenotypic level is a kind of intermediate level that can, to some extent, explain what the fitness landscape actually looks like. So that's sort of one point of view. The other, okay, so maybe a different question would be, could you see, could you see adaptive walks also in phenotypic variables? Of course, what a lot of experimental evolution people do is to look at fitness as a phenotype, and then this is more or less all you need, right? So if you have some experiment where you evolve some organism and you measure its fitness, and then people actually do see that in some cases there are these sort of discrete jumps which you can then interpret as steps of an adaptive walk, and they show that fitness increase. Of course, it's a kind of tautology that fitness has to increase during an evolution experiment, right? Other phenotypes might do more complicated things, but as long as you use fitness as a phenotype, I think this can already be applied.
Okay, so you're saying this picture already, essentially, the phenotype is, you can interpret it as the phenotype already being incorporated?
Yes.
Okay, thank you.
Other questions? Satya?
So considering this correlated landscape, right? So you talked about this Mount Fuji model.
Mm-hmm.
So is that the sort of the most sort of accepted model for the experimental data, or are there other models of correlated landscape?
Well, there's a second class of models that we have looked at quite a bit, which are the so-called NK models. So Kaufman's NK models, which are like spin glass models, where you sort of reduce the dependencies between loci to certain subsets of loci. Okay, and so we have also looked at adaptive walks in these NK models, and there are some other results that one can quote. Whether or not these are good models for empirical landscapes, at least in this early study, this 2013 review that I mentioned, there we tried to parameterize empirical data using these models, and there we found that this Mount Fuji model works reasonably well to the accuracy that these data have in the first place. But I think this is certainly not very much still an open question. I think people also, I think a lot of biologists don't really think that these models are that realistic. But I think to the extent, for the data that we have so far, I think both of them are probably reasonable.
Other questions? Okay, then if not, let's thank Joachim again. Okay, so I guess we should enjoy coffee.
Let me start by saying what is the question. So let us take n ID positive random variables with common density f of x and finite mean. Okay? So I will denote it by C1 like first cumulant. So the mean sum of those variables is equal to n times C1. And assume that this sum is constrained to take a fixed value y. Okay? So the question is, how is the difference, delta, between this fixed value given to the sum and its mean, be how is this difference distributed amongst the random variables, okay? So this difference can be positive or negative, or 0. In other words, if you want to have a picture, the question is how elastic is the system? So you have n random variables. So it's a metaphor, it's an analog, it's not the real system, but think of n springs, and each one is distributed, this length is distributed, and then you can compress them or stretch them, and the question is how they will respond. Will they be all compressed essentially the same, or stretch the same, or can it be that this is the second scenario? So let us look, sorry. So what happens will be the following. If the distribution of those random variables are exponential, it turns out that every random variable will take a bit of the difference, either positive or negative. But if this distribution is sub-exponential, power law, stretch exponential, then every random variable will take a bit of the difference if this difference is negative, or 0. But if it is positive, then there will be one random variable bearing the excess delta. And this is a phenomenon of condensation. So it's the purest way of looking at condensation, which appear, for instance, in the zero-range process. So it's an old subject, which is still active. And it is rooted in the study of the statics of condensing ZRP. So here are a small selection of papers dealing with the subject. There are many others. In particular, there are following ones here. And let's say that in the world of physicists, this one was the first, which was not motivated by ZRP, actually. It was a completely different subject. But they looked at the statics, actually, without knowing it. They were looking at the statics of a condensing ZRP. Then mathematicians came and realized that there was something with random variables, and so on and so forth. So here I will, this subject, which I've just explained, was looked at in detail by Martin, Satya, and Zia. And essentially what I will say will be around this. I will come back on their steps. And I will also take some bits of a paper that we did in the past, which was dealing essentially with dynamics, but we needed some aspect of statics which will be instrumental here. And so now this is looked at by mathematicians, and which what I don't mention here are extension of this kind of work where instead of having one constraint, you can have several constraints, but this is a more complex problem. So here I want to look at the purest problem, which is the one that I've said. And my focus will be what is the minimal account of the theory that I can give. And also, I want to know how accurate are the prediction of the theory. And in what will follow, you will understand what I mean by those two items. So I will do the following. First, a warming up, which is to look at two examples of distribution, an exponential distribution and a particular example of a distribution with a parallel tail. And I will compare exact results, finite n, to asymptotic predictions. Then we'll come back to the theory for general case of parallel tail distribution. So the basics. You have a sum of random variables, and you look at the density, probability density of this sum, which is the derivative of the distribution function. And this is the sum of those density, which are independent, so it's a product form. But you have got the constraint that the sum of this variable is equal to y. Now, if you want to know the conditional density of the random variable given this condition, then you just have to divide this by this, which sum up, if you integrate on y, it will give you 1. So this is the usual form of this conditional density. Finally, if you want the marginal of one of the xi, you have to sum upon all the xi but 1. So you get this nice formula, which is easy to remember, because this is the conditional density that one of the xi is equal to x, knowing that the sum is equal to y. So this is the original one, the bare density, the bare distribution, and it is dressed by this ratio. So fx is f1 if you want. So you have f1, fn minus 1 divided by fn, and the argument are x, y minus x, and y. So it means 1 has got x, the n minus 1 remaining have got y minus x, and you divide by this normalization. So if you look at the conditional average of one of the xi, which I denote like that, you integrate, you take the first moment of this distribution, and so it is necessarily y divided by n, because the sum is y, and you have n variables, so this is y by n, and you denote it by rho. So delta, the difference between the conditional and unconditional, delta, which is the difference between the sum and the mean, is also the difference between the conditional and unconditional averages multiplied by n. Y minus nc1 is n rho minus c1. So it's the difference you see between dressed and bare. So you see that in order to compute this thing, this object, you have to proceed in 2 steps. You compute this distribution, Fn, and this is a very old subject. It's that it has got 1 century. Compute the sum of independent ID variable began, I think, at the beginning of the 20th century, or even before. And if you have got Fn, then you just have to compute the ratio of those 2 quantities. That's all. So just to figure out what is this figure saying, what you are interested in is a dependence on x, which is a variable, and y is just a parameter. So let us look. This is a distribution of the sum. This is Fn. Okay? So here the average is equal, C1 is 2, 500 random variables, and suppose that y is fixed here. So when you say y minus x, x is here, so what you have to do is to follow what is doing this sum when x increase, uphill and then downhill. If you start from here, but you could start from any of those points. So it means that this curve, there is 1 curve per point. Here there is 1, 1 for any case. So this is how to deal with the problem. So for those who know the zero-range process, I have no time to speak about that, but just to remind it quickly. In a zero-range process, the language is the number of continuous variables is the number of sites. The xi are the occupation numbers. This density of individual x is the probability of individual occupation. The average of 1 is the average of the occupation of, let's say, one of the box, let's say the first one, which is usually called rho c. There is a sum of those variables. Y is n, because the sum of the occupation is fixed to n, and so the density is n over L. Fn, the density of the sum is just the probability that this sum of occupation is equal to n, and this is the partition function for L and n given. And finally, this marginal distribution is the density the probability of occupation of a single box, a single site. So this is the language. But I will forget about that and continue. So I want to think from an example first. I take the exponential distribution, which is here, which is written in such a way that the average is equal to C1. So the exact distribution of the sum is explicit. It's the gamma distribution, and that you find by just inverse Laplace transform of f of the distribution of the sum. Here it should be fn is the same. So the distribution of the sum, f, which I usually denote by n, I didn't change the notation on this slide. It's n times, I mean, it's the power n of the Laplace transform of one, of the distribution of one random variable. And so if you invert that, you get a gamma distribution. So if you have got this, it's finished. You have to do the ratio, and you find this expression, which is not very inspiring. But if, for instance, you look at what says this expression for x of order 1, you get this expression, and this is essentially what you find is the initial one, but now you have changed the parameter from C1 to rho, and rho is actually what you impose on the system. So it means that the system is completely elastic, because if you compress it, it will still be exponential. If you stretch it, it will be exponential. So everybody follows, you see? So that's what we are, which is in the jargon called the fluid phase. Okay? Second example. You take this particular form of a power law, a power law distribution, and you see that when x is large, it's, I want to call it, I want to denote it by c to the power 1 plus, which is the usual way of denoting this kind of thing. And this will be the general exponent which will appear later on, which I will call theta. So it turns out that if you take this distribution, the average is equal to 2. Okay. And it turns out that the exact distribution of the sum is explicit. And that was a very cute example given in this paper. So you have got Hermite polynomials and so on and so forth. The derivation is clear. All the steps are very clear. You start from the Laplace transform of this, which is this expression. You raise that to power n to have the distribution of the sum. Then you have to expand this. So this, you put it aside. Then you expand the binomial thing here, binomial coefficient. You have to invert each term, and you rearrange, and you find this very nice thing. Actually, what is not very, what is it? It's this curve. This is for 500, exactly this function, okay? So what to do with that? First, I want to show you a movie of the marginal distribution. From that, we can draw an intuitive picture. Then we will have to do an asymptotic analysis of this exact expression, from which we will infer the asymptotic analysis of the marginal, and we will compare it with the exact marginal, which is drawn from the exact sum. So the first thing is to show you a picture. So here, what I will do, is to show you in log-log what is this distribution. So this is the marginal. The distribution of each one of those n random variables when the sum is fixed. And the sum is sliding from 0 to 8 times n. But remember, the average is 2 for each random variable, so it's 2n for the sum. And so you are forcing the system to be smaller or larger than 2n. So it goes from 2 to 8 times n. And you look at the distribution of the marginal against x, okay? So what you see is the following. So beginning for small values of y, let's say less than the nominal value, which is 2n, you have got essentially, first, it's a kind of exponential decay. Then you see that there is a flat part, which will be the critical thing, then appears progressively. It's progressive because n is finite, so the transition is not instantaneous. But then you see that a dip is appearing, and then you see a bump. This is the scenario. We can redo the same, not in log-log, but in linear log. And then you see this. And it's nice because you see what I will call the deep region. Okay? So let us turn back to this. So let us get an intuitive picture of this. We see three regimes. The first regime is when the difference is smaller, is negative, when rho is less than 2. So all variables have the same status, which means that each one bears a small bit of delta, and the marginal is given by the original one multiplied by some exponential which compresses the system. And what you see here is a denominator. The denominator, is to ensure normalization. So this means that if you take now the first moment of this thing, it gives you exactly this expression. But you see that it gives a relation between the density and this S star. Okay, so S star, this inverse correlation length, is a function of the density. So this is the fluid phase, or democratic. If delta is equal to 0, then you have seen in log-log it was flat. The marginal distribution is asymptotically the same as the Baire distribution. And you see on this expression that S star is 0. Why? Because you have to put C1 equal to, rho is equal to C1, but in order to have C1, you should have 1 here and X here. So S star is 0. This is a critical phase. The correlation length is infinite. And if delta is positive, the excess difference is with a very high probability bound by only one of the xi. And all the other xi follow the Baire distribution. This is a condensed phase. Okay? So now, Craig, jusqu'à quelle heure? J'ai commencé à moins 20, je crois. 25, non? Plutôt? Non, non.
25 minutes.
Ok. D'accord, pas de problème. So we want to analyze this nice expression. First, we go in the bulk. So the bulk is when the sum, the constraint sum, is equal to essentially equal to its mean. So if you look at this expression, let us call that z. So you see that this z is a curve like that. When y goes from 0 to infinity, from 0 to infinity, z is doing this. And so the minimum is at y equal to n, and the value of z is what? It is this quantity, square root of 2n. So you go to books to look at the asymptotics of the Hermite polynomial around this value, and you find plenty of formulas, but you don't need to do that. You can do it if you want to to do an exercise, which is nice. But you can directly go to the general central limit theorem, which tells you that in the bulk, the sum is given by this expression, where when you have rescaled and centered and rescaled the sum, the sum is given in terms of the stable law for index 3/2. C is the parameter of the tail, which is here equal to, in this expression that we gave before, of the one variable distribution, we choose 2 over square root of pi. And so the stable law, it turns out that it is known. It is known in terms of array function. And why is array function coming in the play? It's because the expansion of Hermite polynomial near the turning point involves array function. Okay? So this is a bit, you could say it's complicated, but the Laplace transform of that is extremely simple. That is well known that for stable laws which have got where with an asymmetry parameter which is equal to 1, meaning C plus minus C minus, the two tails is equal to 1. So actually here you have got a tail only on the right, because you have to take positive random variables. So they have got this simple, very simple expression.
So there should be a negative sign. Exponential minus 8.
Minus, yeah.
Below, Laplace transform.
No, it's plus. It's plus. No, this is plus and this is plus. No, it's plus, it's plus. Yeah, it's absolutely plus. Yeah. Actually, I know why you say minus. It's because it is minus when theta is between 0 and 1. Then it's plus, then it's minus, then it's plus, because this number, A, it changes side every time. So the tails, now let us look at, so I open a parenthesis to look at the tails of the bulk. So it's not the tails of the true distribution, it's only to look at the tail of the stable law, just as a curiosity. Actually, it's not only a curiosity, it's because on the way on, you need this. So this is it. So you open a book, or you do the computation for yourself, and you see that the right tail of the stable law is the same as the initial distribution. This is well known, okay? And in some sense, it's a bit natural. Well, in some sense. But this is only true for theta, which is the general exponent of a stable law between 0 and 2. Okay, so the left tail, again, there are formulas for that, but the computation is not difficult. It's always a saddle point of something. It's complicated expression, but it boils down when this exponent is equal to 3/2, which is our case, it gives this expression. Sorry. So if you cast this asymptotic expression in the general central limit theorem, what you see is the right tail, which means for the argument of the stable law large and positive, you get this expression which will appear and reappear. Okay? And for the left tail, you find this expression. So it means that at exponential order, you have a large deviation function which has got this expression. So those are the large deviation of the bulk. Now we want to do the complete work, which is the asymptotics of the complete exact formula, the tail. And so we want to know what are the tails. Now we remember the z of y. Now we are either y is small, I mean it's not small, but on the right, on the left, sorry, or on the right. And in both cases, z, which is this value, which is square root of 2n, is larger than this. So this is easy. You don't even need to open a book. You take the generating function of Hermite polynomials, you do a saddle point, and you find this expression. That's it. That's all. You plug that into the formula. You set y equal to n rho, with rho less than 2 if you are interested in the left tail. You expand for n infinity, and you find this. So now we get the full large deviation function on the left. And you see that if we go to the regime of the bulk, in the scaling regime, in the scaling region, we recover the expression of the previous slide. So this is very reassuring. And for the right tail, if you do the same job, set y equal to n rho with rho larger than 2 expand for infinity, you find this expression, which was the same as the right tail of the stable law. So let us recap. I take an example with 500 random variable, and so the exact expression is the black one. The stable law is plot here. Okay. If I look at the exact large deviations, they are in green, and they follow the exact curve. And the bulk large deviation, they follow, of course, the stable law. On the right, you see that it's smooth. I mean, everybody, the stable law and the exact distribution are the same. So in linear log, you can see it better, perhaps. Exact, with exact large deviation, stable law with bulk large deviation, but on the right, the tail is well reproduced by the stable law. Another thing which is interesting to see is how fast is the convergence to the stable law. So those are 3 curves for those values. And so now we want to deduce from that the marginal conditional density. So again, as I said, you have to look. You start from some point, and you have to go on the curve, follow the curve with x, and that's it. And so what you find is the following. So you see that you have to know where you are on the curve. So there are different regimes of parameter. If you begin by the left, meaning that y is n times rho, but rho is less than 2, delta is negative, this is the fluid phase. So what you will take is the left tail expression, the large deviation function, and you plug it into the formula, and it provides you a very accurate estimate of the marginal distribution that you're interested in. Even if x is very, very large for very, very rare events. If x is of order 1, then you can expand. I have not written the expression, which is horrible, but you can expand it, and what you find is this expression, and it can be recast. Actually, this is an equal sign in this form, which you have already seen before, where the S star, which is inverse correlation length, has got this expression. So you see on this expression that I could have said that before. I forgot to say that this large deviation function is only defined when rho is less than 2. And this reappeared here. For the critical regime, you plug, you use the general central limit theorem, and you find this expression. And when n goes to infinity, you recover asymptotically the initial distribution. And this reminds you of the fact that the inverse correlation length goes to 0. But if you're interested in the large deviation regime where x is very large, then you need to use the large deviation expression, which is here, to plug it into the formula, and then you deduce what you need. Now, the supercritical regime, where delta is positive, which corresponded to this diagram, so you are here in this region, you see that there are three regimes. First, okay, let us see it here. So here is what I want to call deep in the condensed phase. So you are far away on the right. So we have seen what is the expression of this sum. So we put this aside, okay, because what we need is a dependence in x. And now we need to know what is fn minus 1 for y minus x when x is moving. So we have to compare it to delta x. So in the deep is what we saw on the picture, on the movie, is when this distribution is in a kind of valley. So x is essentially parameterized by psi delta. And what you find is that in this region, since x is large, y minus x is large, again, you will use the same deep in the condensed phase expression. You plug that in the expression and you find this. So this describes a deep region where the condensate and, which interpolate between the critical phase and the condensate. In the bulk, then this is given by the bulk, if x is around delta. And so you find this, where this factor is just the ratio of fx of delta to fn. And this describes the hump of the condensate. And if you integrate this on the whole region, you find 1 over n. And this shows that the excess difference delta is bound only by 1x. Okay? And for large deviation, if x is larger than delta, when you are very far away, you went uphill, then downhill, then you have to use a large deviation expression for this quantity. And this is the result. So if you look for, you put all three regimes together, you have 3 bits, 3 parts in the curve. So first, the exact one is dashed. Okay? But you see that the dip, first one, this is a dip. It goes perfectly well on the exact solution. But then you have to take the bulk, which is good up to some point. And then in the very rare event, large deviation, you need to take the third part. Okay? And this is, for me, a bit surprising because when you see how the exact solution converges to the stable law, well, it's not so fast, and here it's very good. So I've not analyzed the thing, but you see that there are compensations in the play. So this is essentially the first part of my program, which was to see how accurate is the theory. But now we are the program is, if you have not got the exact formula, what can you do? Okay? So what I'm going to do is follow the steps of Martin, Satya, and Zia with some detail. And so it means that you have to do asymptotics. Okay? So the outline is clear. In the bulk, you have nothing to do. You have to invoke the central limit theorem, the general central limit theorem, or the central limit theorem according to the value of theta. So all that is for any theta. In the tail, which is not universal, either you do the left, in the left tail, you do the large deviation analysis by saddle point, and you will find this expression. In the right tail, there is no saddle point. We have seen it already. And so you have to do a specific analysis, and we recover what I call the dip in the condensed phase regime. But it will emerge from the analysis. While all what I've done until now was to discover on an exact expression what was going on. Actually, this was a philosophy. You have got an exact solution, you analyze it completely, you do the asymptotic analysis, and now, unfortunately, we have no exact solution, so we have to do everything in the dark, okay? And so what we find is that the right tail is the same as a stable law, if theta is less than 2, but it's different for Gaussian. So I will go very, very quickly now, just telling you what is the philosophy. The philosophy is to think in Laplace. Why? Because, as we have seen several times, the distribution of the sum is just power n of the distribution of the individual random variable. So all what you have to do is an inversion, that's all. You have to invert the Laplace transform of this quantity, which is a log of distribution, which is a generating function of cumulants. This fx has got, in general, when you have got a parallel tail with exponent theta, a structure which is a regular part and a singular part. So here you have a regular part with dots, and the dots correspond to the fact that theta can be big. Theta can be 23, in which case you have C1, C2, C3, all the cumulants will appear. And then you have got a singular part, which is this. So for this quantity, which is the one we are interested in, it begins like that, okay? So if you come back to the example, you see that in this example, this is 1 minus C1, and then nothing else. The variance is already infinite. So the general central limit theorem is very easy. You say that the centered and scale sum goes to a stable law, which is denoted like that for theta between 0 and 2, and it's a Gaussian if theta is larger than 2. And an and bn are parameters that are essentially n to the 1 over theta. It saturates to 2 if theta is larger than 2, and you center by the sum, except if I just, in passing, I quote this case which we are not interested in because there is no average, but it is the same philosophy, okay? And so this general central limit theorem, as you have seen, gives us the bulk. So this you have already seen, but for, of course, if theta is larger than 2, it's a Gaussian. And as I mentioned before, the Laplace transform is given here. So in direct space, you have just to invert. So what we have to know is that if theta is between 1 and 2, the support of the stable law is the whole real axis. If now we want to derive what are the large deviations, then we have to do a saddle point. And so we write down this thing, perform a saddle point. This gives you the derivative of k, and this is a saddle point expression. So we encountered this because I gave it as a result, intuitive result, but actually it's general. And now you understand that S star, this inverse correlation length, is just the value of the Laplace variable at the saddle point. But you see that when rho is equal to C1, we have seen that S star is 0, and here you see it again, but 0 hits the head of the cut of K of S. Actually, I didn't do this comment, but here you see the structure. There will be a cut in the complex plane that you see here, because you have got a square root of S. Okay, so the large deviation function, once you have done you have solved S star in function of rho, you plug it here, and then you have got the result, and you are done. But usually S star is not explicit, then the large deviation function is not explicit, so you look at the scaling regime. So in words, in the scaling regime, what you do is you expand S star to 0, and you find an expression which is what it is. And the gain is that the large expression now is explicit, but the drawback is not valid far away from the far away in the tail. You are in the left tail. And this scaling regime restores what you have seen for the bulk large deviation. Actually, you find exactly this. So there is perfect matching with the tail of the stable law. If you look back at the example, combien? Okay. If you look back to the example, then you see by this method you refine what we discovered on the special case. And if theta is larger than 2, now, if you do the same job, you find the Gaussian form and the central limit theorem. The right tail, which is deep in the condensed phase, I don't give the detail, but it proceeds exactly the same way, which is always the same, writing down the Laplace transform, analyzing it in the right regime. And you find this expression that was discovered in some sense empirically by analyzing the exact formula. And the matching with the general central limit theorem for theta between 1 and 2 is, we already saw that there is matching, but the matching with the central limit theorem for theta larger than 2 is different, because at scale delta square root of n, the tail is Gaussian. And at scale delta for the n, the tail is a power law. And so if you match the two behavior, it will give you, the matching is for delta square root n log n. So last slide, if you go back to the ZRP, it's funny to plot the exact back to theta equals 3/2, the exact formula with Hermite polynomials, with what you find if you iterate, if you find by iteration the partition function of the ZRP. And you see it's very good. As a conclusion, the thing, the general context of this topic is think about around the characterization of condensation in ZRP. And there are plenty of ways of attacking the thing: non-equivalence, equivalence of ensemble, sticking to the singularity, which you have seen in passing here, the structure of the dip also, which I have not commented much, but okay. The 1/, weights in the hump, and analogy with Bose-Einstein condensation. This is not what I've said. It's all the papers which are around this theme. Here, what you have learned is that essentially the problem is analyzing a sum of ID random variables and pick what you have to pick. Okay. And that was understood already by Satya, Martin, Zia. But here, let's say that I took a little bend. What I wanted to know is the accuracy of asymptotic prediction compared to the finite exact results. And you have seen that there are compensations in the marginal distribution, which could be perhaps analyzed. But on the way, we have seen that we need large deviation for the rare events far away from the scaling regime. Okay, what I didn't put in this talk is what happens for the largest. So it's obvious that the largest of the X is also the condensate. And so that was analyzed in a paper by Satya and Martin. And the distribution of the largest is the same as before. So it means that for theta equals 3/2, for instance, it is this stable law in the bulk regime. And again, you can ask yourself, what are the corrections around this behavior? And finally, a thing of interest is the inverse participation ratio, which is also in the landscape of characterizing condensation, especially if you have got IID random variables. Thank you.
Okay, thank you, Claude. Maybe one or two questions? Okay. Okay, then let's thank Claude again. And
who among students, how many of you are interested in the lecture in the morning? Because if not one, okay, so I'll do it. I'll maintain it.
It's called tutoring.
Yeah, all right. So let's do it in here. 8:30, yeah, let's aim for 8, let's say 30:35 until 9:30, maybe a little bit before. So we'll start tomorrow. Okay, so again, I thank you, all of you, for being here. I would like to discuss more ideas here than going deep into the asymptotics, as we have seen in this beautiful lecture of this morning. And I would like to discuss how extreme statistics, rare event, can be compensated by redundancies. That is, you have many copies of the same thing, and instead of waiting a long time, if there was only one, you suddenly don't have to wait so long, because one of them will find, let's say, a small target much quicker than if this guy was just alone. And I would like to discuss this in the context of molecular and cellular biology. So before that, I would like to dedicate the talk to my collaborator who passed away this summer, Zev Schuss. As you know, he started as chief orchestra. He studied music before he moved to the mathematics and application. And I wrote, if for some of you are interested, an obituary on that I posted on the webpage about this journey that from which he was part here. It's called The Terran Children, and so if you're interested in this, you're welcome to have a look on these 10-15 pages that I wrote about his life, both in science and outside science. Okay, so let's go back now to what I meant by redundancy. Many copies of the same object. So as you know, I don't have to elaborate on this for you guys. You have, in statistical physics, in thermodynamics, many copies of the same object. They can be treated as particle, but also in chemistry, when you bring them together, they can make fantastic structure arising from life that we know today as a very complex and organized structure. Here, what I'll be interested in is, in the context of biology, to focus on what particular aspect, which is the redundancy, having many copies, but for transient processes, fast transient processes. And I would like to discuss 5 questions, 5 different topics, basically. Gregory, please stop me 5-10 minutes before. I want to see where I am. I try to go fast, but I don't want to go too fast. So let me just briefly say what we are going to discuss here. Activation, chemical activation and amplification. How long it takes for something to be activated or to be amplified. Because amplification is a very important part of chemical reaction. Remember, in the eye, we can see a single photon. What is the meaning of seeing a single photon? It means the cell can respond and amplify. So there are many processes of this type. And then there is a question which is how long it takes to search for a small target, and what's the role of the geometry when there is one particle versus the case when there are many particles. And then you are not interested in the average time, but the average for the first one to arrive to a small target. And this will be actually the important time, not the narrow escape time as we've introduced many years ago. We saw that it could be important. It is important in many places. But for fast activation, it doesn't play such a role. Then I would like to give some example. So here I would like to illustrate this through one example that we will discuss. Is related to neuroscience. Another example is going to be about trafficking inside a network which is called the reticulum endoplasmic, which has how proteins are moving inside this network for their delivery. And of course, an obvious example is fertility. Why you need so many sperms? Why you have hundreds of millions of sperms per milliliter, sometimes more, sometimes less, and you have one egg? Why this disproportion? What is the meaning? What does this tell us about the process of fertility? And you know that this is a very important and serious problem nowadays, since the number of sperm is drastically declining. And finally, another completely unexpected role of redundancy and extreme statistics is the definition of time. The definition of time in biology. What is the time when cells stop to divide? What defines this? And we are going to see that this has to do with the length of the end of the chromosome, and actually not the length of all of them, but the length of the shortest. So it's a stochastic processes, as we're going to propose, that seems to define the time when the cells stop to divide. Okay, so this is the program of today. Maybe this would have been the program the entire day. I'll try to make short and stop on time. I think I did something. Okay, so let's go to activation. Let me give you some example. So I've been interested along the scale of the brain from the molecular, let's say, to the cellular level. So we are here at, let's say, sub-micron nanometer, trying to bridge the gap to cellular and neuronal networks. And here we are discussing about a time scale of the order of a millisecond to more. So one first example about redundancies is the process of synaptic communication. How a cell communicates to the next one by chemical synapses, it has to free about thousands of molecules, which are called neurotransmitters, that are moving here. So they are at time 0, these vesicles open. You have 3,000 about molecules that have to find small places which are called receptors, and upon binding they open the receptor, and then there is a flow, a current flow. Now you can model this using whatever stochastic chemical reaction model, but what you find is the following, the answer to the following question. What's the probability for one of these molecules to hit, let's say, 1 to 50 of these receptors? It's not that much. Before they escape and they are going to be eaten or extruded from the neighboring cell, which are called glial cells. This is important because if you don't have this, you can have accumulation of these molecules and it can go and activate other cells. So it's very important that they are going to be captured. If you do such a calculation, you do this using narrow escape, you assimilate this as a cylinder, you calculate the probability to find a small hole located on this piece of a narrow cylinder. You can estimate this probability as a function of the different elements. A is the size of the small hole, R is the radius, L here is the length. You get some formula, but the answer to the question the probability is of the order of 1 divided by 1,000. Now, if you multiply or if you account for those molecules, suddenly you recover a probability which is of the order, let's say, half 1. So suddenly you see that the redundancies is important to make sure that your process works, that you are going to encompass the fact that the vesicle, when they release or the neurotransmitter, they don't know where the receptor here they are. So you need this redundancy to solve this question. So another example is, again, how do you create an amplification? You need 1 or 2 molecules, the first one to arrive to a specific receptor, to open this receptor. Then you have usually a high current, and this is the principle of amplification in many cellular devices. So again, I want to go through some example. So suppose at time 0 you have particles, in that example that are calcium. Calcium is flowing by diffusion, and you ask how long it takes for this calcium to arrive here to this specific place. And I will come back to this specifically. Another example, it's another type of molecule. It's another type of signaling. It has to do, why people are interested in all of this type of question about calcium or activate here this IP3 receptor, because it is associated to memory. And it's not clear how this is done today. What is the process by which suddenly, after you see something or you spend enough time on something, you're going to remember it? The idea is at this level of a synapse, this is where you get the chemistry converted into cellular memory, the process of which remains unclear. But we think that through this statistical physics of this molecular interaction, we can understand something. Again, here you have this receptor activated. IP3 is the name of the molecule. It has to go, and it has to reach, and only the first one who will arrive will give us the time scale, not the mean, not the rate usually computed from the Smoluchowski framework. And then it activates something which is associated to more calcium release. And this we have already discussed. The role of redundancy is to make sure that you are going to have this signaling. Okay, so now I would like to focus on the first example. Again, we are back to the brain. This is a synapse, a presynaptic neuron connecting a postsynaptic one, and we'll be interested in this postsynaptic part here. So I have to tell you, now this is how things are studied in the hand of experimentalists. So those are the structure. This is where the connection occurs. So for example, you can ask, why you need a specific geometrical microdomain instead of having a direct connection here? Why you need something else, a sort of geometrical isolation? And on this specific isolation, you see this yellow marker. It is a marker for a subcellular compartment. That is, there is something here specific, but we don't know exactly what this structure is doing. So I started to be interested in this through a collaboration with my partner at the Weizmann Institute in neuroscience. And they had this following general picture that you have this structure. Inside you have this yellow part that I just showed you, which has to do with calcium modulation. But how? It was not clear. So to study this, what they did is they study transient activation. So let me just describe the experiment so that you understand what I'm saying. At time 0, suppose you have a certain number of particles that are calcium that are released inside this head. In blue, you measure the amount of calcium inside this structure. In parallel, you measure in red what happened at the base, right? so blue is what happened here. Suppose you release 200 particles. And here you look at the function of time, how many particles arrives. So you have a certain decay in the blue and a certain race time here in red. It turned out that the race time was the order of few milliseconds. And this is when you have this structure, we don't know what the structure here, and what we are going to try to do is a sort of reverse engineering problem, basically based on transient property. Can you infer how the structure is working? If such a structure is present, you have this. If it's absent, there is nothing. So the structure probably matters. Although it appears like an obstacle, it should prevent particles to move. And when we did simulation, just Brownian simulation, as you can see here, this is the decay, the blue, but the red, which is a different scale, we saw nothing. So diffusion cannot account for that. So then we could not understand that because this was the idea of simple diffusion, which could be the fastest signaling pathway to go from one point to another. What could be faster than that? So we went back, and then let me just remind you briefly the concept of narrow escape and the role of the geometry, the mean first passage time for a particle to find a small hole. As shown by many people, briefly mentioned here, it has to do with the surface, diffusion coefficient, 1 over log of 1 over epsilon in dimension 2, where epsilon is the ratio of the absorbing patch to the total boundary. In dimension 3, it's a bit different. It has to do for a circular disk. The V is the volume of the domain. This diffusion coefficient, A, is the radius here of the absorbing one, and this is the leading order term, and then you can continue the expansion, and what comes into the expansion is the curvature, the mean curvature at the center of the patch. If the patch is, has a shape, it's much more complicated. For example, you can start with an ellipse, try to move the ellipse in a very elongated ellipse, and you have different type of asymptotics. For a square, we worked on it many years ago with there. We never published it. Because of the singularity, you find actually a different power law. And so another example of the role of the geometry is if suppose you have a cusp. Suppose you have to escape and find here until the end of the cusp. How does that affect the mean first passage time? In dimension 2, it was log. But if you have here this shape, suddenly it becomes 1 over square root epsilon, where epsilon is a side, and r here is the radius of curvature. If you are on the Riemannian surface, if you have a certain shape which satisfy a certain type of decay, the time is proportional to 1 over a to a power. And so you can see the power in the mean escape time. And in dimension 3, basically, you can have this with a circular symmetry. Instead of having 1 over square root of a, you get 1 over a to the power 3/2, which is different from the classical escape, which is 1 over a in dimension 3 if you just have a disk. Another interesting phenomena is suppose instead of escaping here, you add here a tunnel, a long tunnel. Instead of having 1 over a, you see that there is the time is much longer. It becomes 1 over a square. L is the length here. Omega is the total volume. Because of the recursion, the particle will go back and forth from this domain, escape, and can go back. And this is the reason for this term. So basically, it was worse and worse. The time was longer and longer as we added geometry. And the time scale we found was hundreds of milliseconds, nothing to do with 5 milliseconds. So where that was coming from? So for this, we started to envision that probably it has nothing to do with the mean. And maybe there is more chemical processes coming, but yet, what is the fast messenger? So then we started to look at the process itself. If you have many particles, maybe what we need to look at is not the average to arrive, but the average for the first ones to arrive. And I will explain why. So has already been mentioned. If you have n identical particles, here they are Brownian motion, the mean first passage time for the first one out of n to arrive is connected to only one particle at the power n. And to calculate the time, you have basically to go back to the diffusion equation with a small patch reflecting boundary condition. And instead of looking at the long asymptotics, you have to look at the short asymptotics, short time asymptotics. And the probability distribution has to do with the survival probability of the n-1 particle multiplied by the flux here of the particle to the absorbing hole. And again, I'm not mentioning everybody, but many of people in this audience have contributed to the framework of the extreme statistics. But here we had to look at this in 3D or in 2D in the context of narrow escape, how long it takes to find a small hole. And basically, this is to remind you the narrow escape. It has to do with the volume. And when we looked in dimension 1, dimension 2, or dimension, sorry, it means here n much bigger than 1. In dimension 1, 2, and 3, let's look, for example, in dimension 2. The time it takes for the first out of n to arrive has to do with the minimum distance, not anymore the volume. It's because what you are using to solve this in the short time asymptotics is the ray method, so it's the ray. And the ray is the geodesic basically between 2 points. And what you see here is you get the log of n. This is what you get usually when you have n particle in dimension 1 looking at the first one. And then you have log of 1 over epsilon, where epsilon is the ratio of the absorbing to the total surface. And so this was telling us that, first of all, you don't have the same geometrical property than the narrow escape. You shoot, the fastest particle shoot, if it can, toward the target. And you can see through the log the contribution of n and the fact that you have a narrow opening. And you can do the same in dimensions. I'm sorry?
What is the initial condition?
You suppose you start here at the center. P0 is here. Uniform, yeah, sure. But this was not what we are interested in. Because, this is a good question. Because when you go to the example of the dendritic spine, you enter through a narrow channel. You enter through one spot, which is very far away from where is, I'm going to explain, where is the place where you need to find the target. Okay, and then basically, if you have an obstacle in between, you can see that still you can have a trajectory that are concentrated near the geodesic. And the geodesic is not anymore the straight line because you cannot go. And so we started to study that numerically. And you can see that the length is actually concentrated along the length of the shortest geodesic. Okay, partial conclusion, effect of redundancy, decreases arrival time, use a different geometrical fixture, allow to find target before escape away, as we have seen. Now, we did the simulation here, and I would like to come back to your question. And so here we started at this position. You can start at that position, but that was not that important. And then we wanted to understand what is the mechanism by which you are going to signal very quickly here at this place. And we said it has to be through a process associated to diffusion. However, we noticed that the structure here can have specific channel which are called ryanodine receptor. That is, if 2 calcium ions are bound to this, they release calcium, assuming that you have calcium inside, and it happens. So then the question becomes, all right, so maybe what happened here is not that you wait for all the calcium to go from here to here. You don't care, or the nature doesn't care. What happened is that you need the first 2 calcium ions to open one of these channels. And then you'll have a mechanism of amplification, because what the calcium you have seen, I mean the calcium they have observed experimentally, is not the calcium that was flowing through here, but through this amplification. And the signal is the fast calcium ion that move from here to here. And you don't have to wait half of the population to be there. And so now we looked at the property of the channels, calcium-induced calcium release. When 2 calcium arrive, it leads to this avalanche. And so this is to describe there is another property of a channel that do the opposites, that pumps in. So you put the two together, you do the simulation, and indeed what you find is that when there is no of this mechanism, nothing happens, but when there is this mechanism, blue and red, you see a time scale of the order of milliseconds. So this was a possible explanation for the experimental data.
So they sort of line up until someone opens the door. So
they don't line up.
So
they hit, they find, and that's it.
I see. So there is no accumulation there.
No accumulation.
They just keep going.
Sure. And if they miss a target, they miss a target. So then we looked at the distribution of arrival time for the first one and the arrival time for 2 ions to one of the target. And we indeed found something that was very satisfactory in terms of the time scale of the experiments. And now we propose a certain organization of the channels that have speak a little here, but you can see in this picture, we put this mechanism just at the base. Just you need this extrusion mechanism just at the base, not everywhere. And this is what we needed for the simulation, and we put everything else, the other one at the top. And we looked at the literature, nothing was documented on that. So we asked our experimental partner, is it a pure invention or is it true? And to our surprise, they did the experiments, and this is exactly what they found. They found that this structure was exactly enriched, as you can see here at the bottom, compared to what you have here in the middle or at the top. And the other one was the opposite. So I think it was very nice because the simulation and the theory led us to the prediction that they double-check experimentally. Okay, let me skip the conclusion. I have already said most of it. Maybe just to insist on one part, the extreme statistics is defined by the first ion to arrive, and it gives a time scale, and which is very different from the diffusion and the measurements. Okay, so now I would like to show that this is actually one example, but there are many examples like this. So recently, using many amount of super resolution trajectory data, basically I give you trajectories and I give you hundreds of thousands of those trajectories. In a structure like this, what do you see? What can you extract? By just coloring, painting the trajectories according to their displacement, the x of t plus delta t minus x of t, and you take the absolute value, you take the length. What we saw, just popping in the figure, is that you see low velocity, low displacement inside what is called nodes, while high velocity occur between nodes, just by painting, nothing else, which allowed us to find a new type of network flow redistribution. No diffusion. It was fast shooting in between nodes and restricted in nodes. More than that, between two nodes, there was some kind of waiting time. The particles, we're talking about real experiments where we got data on a structure that we had no idea how it works. So the particles are waiting at the node, and then you can see here, for example, blue. The blue is shooting, so it goes in one direction, then it stops, and then it goes to the other direction. Suggesting that so what is this structure is the endoplasmic reticulum, proteins are synthesized somewhere, and they have to traffic inside the network. And the question is how this particle move from one node to another. And now the question becomes, I mean, the question that we would like to answer, how long it takes to go from one node to another. How long it takes in average, or how long it takes for the first one to arrive. Those are two different timescales. Okay, so for this, we started to create a graph. from the data, look at how nodes are connected through these arrows. And then, so this is an example of where we abstract this into this honeybee type network. And what we looked at is what is the time and the path between two nodes. And again, in this extreme statistics framework, we had many particles located here. How long it takes for the first one to arrive there? And again, you can see that what is associated is a geodesic on the graph, associated to the distance on the graph, and log of n is the number of particles. And here, the diffusion coefficient here is actually associated to the rate to switch between the node when you are at a point here. And this depends, as we're going to see in a second, if you are allowed to cross. So this is an example of how this the trajectory, the length of the trajectory concentrate near the length of the geodesics. But what we found was depending on the switching rate. So there is a rate which you have to wait. That is, if you are not allowed to go from one node to another, you have to wait. But since there are 3 nodes, and if you are located at one node, sometimes you are in a situation where you cannot take any of the 3 because you are not at the right time. And so what we found here is a sort of new type of distribution of molecules. It has nothing to do, I mean, if the switching rate is fast, you have basically something that equilibrates in classical diffusion process statistical physics. But if the switching time was long enough, the particle have to wait. And we found out that although they are allowed to move as independent particles, they move together in packets. This was quite surprising. And so they go from one point to another, nothing happened, and then suddenly they arrive per packet. Again, showing that this arrival of the first one here has nothing to do with the classical description of the statistics.
So it would be correct to call it just arrival in groups?
Yeah.
What essentially defines
but we didn't impose that, right? We looked, and when they arrive in groups. That is, we didn't know in advance that it was... Yeah, absolutely. That's right. Completely independent. Okay, so I would like to discuss a little bit about our fertility, where we did some calculation, again, about the same question. Again, after the spermatozoa are located here at the entrance of the uterus, it's called the cervix, there's a narrow region, they have to find, depending where the eggs is located, a small, narrow a point where the eggs is. And we know that the first one who will arrive will fertilize the egg. So it's, again, a problem in extreme statistics. And I've been asked many times how to relate the number of sperms to the specific species. Why you need such amount of number? Why not 10 times more? And you know that actually, I mean, from study, if you decrease the number of sperm by 4, it's already a cause of complete infertility. And by 4, you still have millions. Why? Why is that? Where these numbers are coming from, and what does it tell us about the process itself? And I want to emphasize that there is a lot of literature about the fact that things can be guided, that the temperature can guide them, or the rheology can guide them. It's actually true only, for example, for the chemotaxis, if you are very close, but if you are centimeters away, which has happened in mammalian species, it's not true. And this is why you need redundancy, because they have no way to know where the egg is located. So how long it takes to find the eggs by the fastest spermatozoa? So this isn't published data. I had this for about 8 years now, trying to find out relationship. Just I plotted the number of sperm versus the volume of the uterus. So you would say, if the uterus is big, you would need more sperms, right? I mean, this would be logical. And yeah, there's these trends, but sometimes it is also broken. Also, there are 2 groups here. There's the groups of the small animals compared to the bigger one, like horses and bigger ones. Can we say, I mean, this is just empirical, putting empirical data on a graph. Then, many years ago, I asked my collaborator, what are the sperm looking in vivo? Not under the dish, and you can go on YouTube and look at many of those movies. And people model that by Brownian motion. Say, no, it has nothing to do with Brownian motion. It's very persistent. Those are movies taken from spermatozoa inside the uterus. And they are very persistent. And so at that time, we found out, all right, maybe we can do a very elementary model where suppose the uterus, I mean, not discuss at this point the uterus. Suppose you have, you look at the first time when you shoot and you are reflected at a random angle, how long it takes to find a small hole. So we looked at this in dimension 2, dimension 3. And what turned out that in dimension 2, it's basically like a billiard problem. It's 1 over epsilon, where epsilon is a sign. Dimension 3, it's epsilon squared. And it was very hard to do the case of the uterus, where you want to approximate it with cusp. We did some simulations, and it turned out that the best fit, this is what we could do, is constant epsilon to this power. Where this power is coming from, I have no idea. No, it's not Brownian. You shoot. This is the trajectories here. And then we said, all right, what about the extreme statistics? What about the first sperm that arrives? What's the goal of extreme statistics? So that we can. So you have a distribution of arrival. You look at the beginning of the distribution, and you can see that actually they shoot through the rays. They move along these two rays and find the target, assuming here the target was the two ends of this construction.
Maybe you have 5 minutes.
5 minutes, okay. So basically, for this project, this is where we are now. We're trying to understand the role of many sperms is to select the optimal path. It's not that they are going to accelerate the time, because the time is given by the speed. You cannot exceed the speed of their maximal speed. Actually, let me show you that before I switch to the other question. We're not satisfied with all of this, so we said we need to see things now and construct a microenvironment for sperm. So we design micro chambers, and actually we saw deviation of what I just showed you. This is an example of what we call sperm diffraction. Sperm diffract. What does that mean? It means that if you look, so I spent afternoons in front of the microscope. I didn't set up the rest. But looking at how the sperm were escaping this domain, and we found that there was a dispersion in the angle. There was a dispersion of the angle, which we didn't predict and we didn't saw before. And we characterize this dispersion of the angle. And so you see, they can go along an obstacle, stick along the obstacle, like the theory of rays in the 60s, where people looked at this. And then before they depart. Okay, so we're still constructing here to try to find out an analysis of extreme statistics for the first one in this framework where we have these rays and look at how they concentrate along this optimal path. From what we have in this paper that we published a couple of years ago, we estimated from numerical simulation that the fastest would take 20 minutes to arrive to the egg. And this was more or less in agreement for some cases in the data that was published 50 years ago. This is a good question. It depends on it's usually a couple of days, but it depends on the environment of the uterus, at which moment it entered the uterus. Okay, so let me move on with the 3 minutes that I have left to a completely different question. Why time has to do with redundancy and extreme statistics? Time is what we have learned from classical physics, from general relativity, how time can be connected with space. But how time for cellular biology, how this is defined? And this was a question that started probably 30, 40 years ago. which was awarded to the Nobel Prize about 10 years ago for people who discovered the role of telomeres. Those are chromosomes, telomeres. You see the yellow spot? Those are the end of the chromosomes. Surprisingly, in yeast, they are clustered together. So if you have, for example, 16 chromosomes, you have 32 telomeres, and those telomeres, the center of the chromosome is attached somewhere, but then they can cluster. So, but we're not interested in that here. What we're interested is across cell division, once cell divide, the length is decreasing unless there is a specific molecule that comes to increase it. And it is, as shown here, this is called the telomerase. And this leads to a sort of asymmetric random walk. The question is, what is the time to senescence? When is a sane line going to stop dividing, which is considered as a death? If a cell is dying, it's unimportant as long as the next one can divide. But if none of them can divide, that's it. What defines such a time, and how senescence is related to the number of cell division? For example, you say, if I divide 10 times, if you know that you have a certain amount of time, then you know how long how many divisions are left. We're going to see it doesn't work like this, and there is a random component into this. So for this, you have to make a model where at time, at division n+1, you said the length of the telomere can be shortened by a certain amount, or increased by another amount with a certain probability, and this probability you can fit to experimental data. So you know this probability, you know A, you know B. But you know that B is much bigger than A, and this occurs, that is, you decrease, and as you decrease, the probability to increase will suddenly increase, but you can increase from a lot until you decrease. So now you can imagine that this process of division is not something that will be proportional to just dividing, because you have this process of suddenly big increase, big jump. And so another thing which is important that we focused on is that we suggested that the time for this to happen has nothing to do with the length of the telomeres, but has to do with the length of the shortest. That is, you count and you look at those telomeres, and then you have to look at the minimum length among whatever you have, and look at the statistics. And so this is to show these different statistics. And at that time, what we were interested in is maybe there is a gap, a statistical gap between the first and the second one. And that's why the first one is important, and the second one not necessarily. This is just looking at the steady state, looking at this at steady state. And so you can solve, I mean, if you want to go analytically, you can calculate this probability distribution at steady state. You solve what is called the classical Takacs equation using this probability. I've added here another random component, which is the fact that you can increase with a certain variability, and you found out this classical gamma law. And then you can look for different parameters, what would be the distribution. So to look at the statistical gap, basically, you look at the difference between the first, the shortest one, and the second one. And what we found at that time is that the mean length of the second divided by the mean length of the first one is actually converging as n is large, the number of telomeres is large, to 1 + 1 over alpha, where alpha has to do with this beta, and beta is related to a constant in the problem. So yes, there could be a kind of gap imposed by the chemical reaction of the process. And here you can see the shortest, the second shortest, and you can see here, this is from the experiments, how indeed you can have really differences between the lengths. So, but this is not enough, and I want just to take 1 minute, and that's it, I promise. Having statistics of the steady state is one thing, but this is not what we are interested in. What we'll be interested in is what is the first time, the first division, where the shortest one reach a threshold. Let me repeat. you have cell division, you look at the shortest one, and you are interested, when is the shortest one shorter than the threshold? And that's it, you stop. So we are now back to a mean first passage time problem for the shortest. And this is not easy to solve. So you can formulate this. So those are the simulations. This is examples. This is the mean. You average this, you get the mean, and you go this is extreme statistics. And what you are interested in here is not the first time that this reach a certain threshold, but you're interested in this behavior of the red one, not the average one. Okay, so for those of you who are interested, since I see that I have to stop, you can formulate the mean first passage time in this asymmetric random walk. This is very classical. You can use some kind of Kramers-Moyal approximation to express what is the mean time for, I'm not talking about the first one, I'm talking about 1, to reach a certain threshold. And what we saw, I will finish with this figure, is that there are two regimes. One regime where the cell divide, and it's really, you can read for the number of cell division, you can read how many division possibly are left, until you reach this this equilibrium where you have the population can wait there. And then once it is there, there is some kind of survival. There is something that allows the cell to survive the deterministic number of division that they should have, and it is calculated by the first time you are going to reach here a threshold, and you have to go over this barrier of potential. And so the time of division is not a deterministic linear process. Time has to do with, the time of number of division has to do with a stochastic process, which is more or less at this stage, phrase in this question, escape through a potential barrier for the shortest one. Okay, I'm going to stop here. We have more. And again, I thank all the people that work with me, and especially my collaborator for 20 years, Zev Shus. Thank you.
Okay, thank you, David. We have time for a few questions. Joachim?
You mentioned this in the context of the sperm, but I guess this is true in general. Generating these redundant molecules is always costly, right? So are there indications also for other processes that evolution has somehow evolved so that this number is sort of optimal, so that it's close to the minimal limit that you actually need for the precision?
This is a very interesting question, is why these numbers? If you had too many, possibly the process would work too good. And maybe this would lead to overpopulation. This way of understanding through evolution, I know very little about this. It's not my field. But there is good question here for people like you who are interested in this evolution to think about. I think it's also very timely.
Yes, please.
Do you know anything about the topology of these geodesic lines? Is there always one line? There can be several lines?
Okay. Short answer, if you have a symmetric picture and you start everything symmetric, you have two geodesic. We looked at what happened if you move the initial point asymmetrically. It seems that what contributes the most is the shortest geodesic, although you can have two, but the shortest one does contribute the most. And this is where it's the one taken by the particles, the fastest to arrive.
This is the one that you see?
It's the one we see.
Right. Okay. So you can have caustics in the pattern of this line.
This is a beginning.
Other questions? Yes, Eli, maybe you can.
In extreme value statistics, we always have the limit of large numbers. For example, in the model of the telomeres, you have only few. So the question, generally speaking, is the asymptotic limit reached, or is it something that works and biology doesn't care about the extreme limit?
16 for me, in that context, is infinity. So I understand. This is what I assume doing the statistics. That's why we're trying to be careful and look at simulation when we can. Because if you are not, if 16 is not enough, this should appear in the simulation. At least we should see some deviation. I do care about this, but for the asymptotics, this is what we have for the moment. I don't know how to go, for example, to intermediate regime if the intermediate regimes appears here.
Okay. So I'm actually with the Naval Research Laboratory. It's a mistake that they put down University of Maryland, of which I am a research associate, but NRL does pay me to do what I want. So what I want to talk about are extreme events, but rare events, more or less, in networks. Okay, and I'll start by saying that most of this work that I'm going to present today is done by my former postdoc, Jason Hines, who just was awarded the Jerome Carl Fellowship. So here's an example of a very large event. So the year is 2003 in North America. Here's a satellite view of the lights that are on. And this is about 20 hours before the blackout, and then 5 hours after the blackout, the whole seaboard is dimmed. Okay, so this is Long Island. I grew up there. And you can see it's totally blacked out, along with New York City. So the interesting thing about this is that if you drill down and ask the engineers what really happened, you find out that it's a single wire failure, right? So you have a network of power that's connected throughout the North American continent here, and one single wire causes a problem. Okay, so a link causes a whole problem. That's a small perturbation leading to a huge event. This is the kind of thing I want to talk about. So there are many examples of large changes of very rare or infrequent events, but you get these very drastic qualitative changes in the dynamics. Here's an example by Laura Billings' student where they studied Ebola, and so they were looking at the optimal paths in which the disease goes extinct. And so they plotted here essentially the number of the fluctuating infectives here, and you see it sort of follows this optimal path before it dies out. Okay. Another example by Alison Motter's group is in switching and reaction networks. Okay. And so here you have a genetic network. It's highly complex. It's very high dimensional. And essentially what you have here are stable equilibria where the perturbations can sort of push you from one well to another. So most of this is known to this audience. There's other types of power networks that are being considered right now where they're attaching renewable energy sources to the network externally, and so it's driving these networks to fluctuate wildly. And finally, we have percolation problems. So if you have a food web and you start randomly pulling out various kinds of nodes or links in the web, at some critical value, you start to see a discontinuous change in the damage, and the whole collapse of the web falls apart. And of course, if you like politics, this is the congressional blog during the 2016 election, and whenever somebody released something that was unfavorable, you get a big change in the opinions. So you have an opinion network here. So all these problems here exhibit very rare behavior, okay? But it's due to small fluctuations, okay? So this is sort of the mantra that we're looking at important problems in network science, okay, that are rare. And the frequency of occurrence might be small, but the consequence can be large. So let me fix ideas a little bit to lay out some of the framework. So we want to talk about networks. Okay, so we have nodes and we have them connected by links here. And so you might have some particular collective state that you're starting out in. And due to either external or internal fluctuations, you start at this state, and some of the nodes and or links will start to change, okay, in small ways, until eventually we become something that's a new state that's disordered or desynchronized or possibly extinct if you're thinking about epidemics. And so We're interested in trying to quantify the time it takes to get there, but also the mechanism. So if we understand the mechanism geometrically, then we can possibly import controls. Okay? So you have different kinds of noise sources here depending on the applications. It could be internal, it could be a thermal bath, and the like, or parametric. So here's an example of what I'm talking about for the extinction process. So here's some coordinate as a function of time. And so you see random fluctuations oscillating about a mean, which is going to oscillate very long time. And then all of a sudden, boom, the system drops out and the coordinate goes to 0, at which point the dynamic stops. On the other side of the coin, you could have switching behavior where you have two active states. And so in the network, you have a coordinate here, and it's oscillating about some mean value, at which point it switches to some other mean value. Okay, so if you take enough time series of these particular pictures, then what you can do is you can create probability density functions. So if you look at the coordinate value here, you can ask what the probability is, and you can run these things numerically for both extinction and switching. Okay? And there are a lot of people who have done this in the past, so this is all very well known. Okay, so what we want to do is look at the situation where these large fluctuations occur as a result of small noise that are pushing them into faraway states, okay, every once in a while. And we want to be able to come up with the general approach for the optimal path. So I'm going to take what's known for very homogeneous low-dimensional systems that we've studied in the past and push it into the realm of network science. Okay, so roughly the outline of my talk is just going to be this. I'll talk about different kinds of discrete stochastic networks. So I'll talk about both extinction and switching. And then I'll talk about how to implement control fluctuations so that if you want to externally target some particular node and or set of links, you can change the dynamics in an exponentially strong way. So let me start with the mechanics. Okay, so here's a problem that has been studied ad nauseum. So we're looking at an epidemic, and there are susceptibles and infectives in this particular population. Okay, so this is node I and node J. Okay, so the red are infected states. So through a mass action term, if S and I come together, there's a contact rate beta here, and that multiplied by a connection matrix. So it's a binary matrix. So if I and J are connected, then there's just a 1 in the ijth component. Okay. And so there's some that governs the rate at which this converts to a new infective. Okay? On the other side of the coin, you can have the infective population actually start to recover in some unit time. So we scale out this recovery time as our unit of time. So in the mean field, what happens is that you have infection density versus this contact rate here. And so at some particular parameter here of beta lambda equal to 1, where lambda is the largest eigenvalue of the connection matrix, you get a bifurcation to what's called an endemic state that's attracting. Okay? And the extinct state here below that threshold is going to be attracting but unstable above that threshold. So this is all well known and thought out about. And the internal noise here actually comes from just the mass action term. So the probability of people coming in contact with each other. And the other example I want to talk about are opinion dynamics, which can be thought of as a spin problem from physics. So you have red and blue here with different opinions. You can see that there's some majority here that has a probability of causing this middle node here to switch to the red from the blue. And there's some energy that's taken to govern this particular reaction here. That's a function of the beta and some contact matrix that governs the connection of the network. So here's an example. So the difference here is that this is more of a pitchfork bifurcation, right? So you have a disordered state at 0, okay, and you can go to one density state or the other. So there's a choice here. So what we can do is we can look at real networks. So people have been collecting data now for the last umpteen years, and trying to quantify what these networks are in various situations. So here we have a high school network. The circles here, the larger they are, the more connections or degree they have. Okay? And on the other side of the coin, on the opinion network, we have Facebook groups that are just based on friends lists. Okay, so here's an outline of what we've done. Some of the people in this audience here know this really well. Actually, one of them has taught me some of these things for simpler systems. But Mark. Okay, so you start with some observable, and you construct a mean field based on that approximation. Okay, and so you'll have some very high dimensional state variable. Okay, could be just nodes, could be nodes and links. So you have maybe millions of them. Okay, so then you try to write down the master equation for the probability density of finding that particular state at some x and t. Okay, so we're looking at some particular network. It's going to go through some point which is going to be driven by the noise, at which point it's going to roll into some new state. Okay. So you can figure out what the rates and increments are, just approximated by mean field values. So you write down this very complicated system. Okay, and then there's a small noise parameter. I'm just going to call it epsilon here. And then we can use a limiting perturbation theory just based on WKB solutions, where we make the ansatz that the density depends exponentially inversely on the noise, but there's a function S that we'll call the action, just like mechanics. Okay, and this is very nice, because now I've taken a stochastic problem and I'm going to turn it into a nonlinear dynamics problem. So the action X just has to satisfy this Hamilton-Jacobi equation, just given by this, which is well known to these, and P is just going to be the conjugate momenta to that particular state vector. And so you can write down equations of motion. So this is great. You have a nonlinear system, but it's in a really high dimensional space. Okay? So here's an example of what that looks like for the extinction problem. So here's the contact matrix and this contact rate beta. Okay, so this term here is sort of the susceptible of the ith node. Okay? The conjugate momenta are sort of a measure of the effects of the noise on the system, and they appear in these horrible exponents here. And this is the recovery term, okay, when you're going from infection to susceptibles. Okay? So you sum up over all these things. You have a huge system of equations. Okay? And here's a sketch of what we kind of want to look at. So how to get this action here means that you have to solve this with respect to certain boundary conditions. Okay? And the devil's in the details when you think about the boundary conditions here. And I'll address that later, but essentially this is, this is the sketch. So along this line here, that's the noiseless case. And so that's where your endemic state is, which is stable. And here's the extinct state, but it has a non-trivial momentum here, right? And what's interesting is that you've created everything as saddles at this particular point. So if you're a dynamical systems guy like me, you say, aha, this is a heteroclinic orbit, right? And so you can get all kinds of interesting global analysis results about this. So now you can find S, that's just a line integral, okay, coming from the Hamilton-Jacobi equation. And so you're good to go. Okay, so that's the holy grail, because once you have S, you've specified everything. You can specify the density. You can specify the time it takes to go through some unstable state before it switches. Okay. So here are some takeaways. Okay, so we have a discrete space on a stochastic network. Okay, we've doubled the dimension, but we've made it deterministic. Okay, the mean field theories are just special noise manifolds. Right, so when you're looking at the mean field and you take away the noise, you're on this special manifold on which this deterministic dynamics happens. And so here's our philosophy for this talk, right? So if you have network dynamics that has new physics, okay, even in the mean field, because noise is going to push you off that, you'll have rare events that will be new, okay? And so these are some examples of some of the work that others have done, Mark Dickman, Michael Ossoff, and Baruch Murson, who's here also, and then some of our recent work that's extended those results to full-blown networks. So let me go back to these examples where we've actually taken real networks, okay, and dumped some of these dynamics on it. So here we've taken the high school network, and we've just produced this probability of observing an averaged infection state, okay, and that's in blue from just the simulations, and the red is the theory, okay, so we can predict what the probability is as a function of the state of the system, and so you can see how it falls off exponentially fast when you're trying to look at the extinct state. Okay. On the other side of the coin, you can do the same thing with the majority switching or the spin model. So you can see this peak here, and again, the red is our theory, and it goes through 0 where the system will switch to some other majority. So I mentioned something about the boundary conditions. So here at the extinct state, the momentum is not 0. Okay? And so this is because it's a quasi-stationary distribution. That's the approximation we're making when we solve the problem. And so there's very little leakage there due to just the quasi-stationarity behavior of it. Okay? Over here is the endemic state that you observe, which has a momentum of 0. Okay? So the boundary conditions are different here for the extinct state than they are here, for example. So here, the minimum actually has an equilibrium point, which is a saddle point where the momentum vanish, right? And again, the peak here, the peak here also satisfies just the momentum equals 0. Absolutely.
In a network, you have many of these differential equations for the coordinate and for the momentum.
That's right.
Right. So how are you doing it numerically? You need to find an instanton, and you have like 1,000 by 1,000.
Right. So there's a trick we have that is a model reduction procedure. So essentially what you do is you look at the degree centrality. It's sort of saying, look at those nodes that have roughly the same number of connections. And so you can bin things up this way, okay? So you can take, I don't think I have that slide here, but it might be in my spare set at the end. I can show it. And so what you do is once you bin that up, you can go, let's say, from 1,000 down to maybe 30. Okay, and so that's how we do it. And we retain the fidelity. So it gives you the same results as if you tried to solve for the full thing. So it's a model reduction technique that's based on the structure of the connection matrix. Okay, so this kind of looks like it's old stuff, but here's the new thing, okay? So we're interested in trying to understand what the topology of the network does when you're near bifurcation. So if delta is the distance away from the bifurcation point, in other words, if I go back, where is it? Here, right? So this is my bifurcation point here. And then, okay, and k is the degree distribution of the network. I can show, if you work really hard, that you have this k squared over k cubed here, okay, for the endemic state, and then you have again something that has a low order divided by a higher order distribution. Okay, so it's a measure of the heterogeneity of the network. So the denominators here become larger as the network or the degree distribution on average gets wider. And
you're probably close to the bifurcation.
We are close.
In both cases.
Yes, yes. This is all done. Yeah, you can't do it far away. It falls apart if you go far away. Okay, so delta quantifies that bifurcation point in terms of the connection matrix here on the contact rate for both cases. Okay, so how do we get this result? So this is a sketch of how we do the analysis. So first we look at the boundary, okay, and we expand everything in terms of delta, this distance function. So for example, if beta is the critical value at which the bifurcation occurs, then we perturb that by adding delta. And then we look at the conjugate momenta as a function of x. Okay? So we want to do this line integral, which is PDQ, right? So to lowest order and delta, we look at that. So what does it look like for extinction? So you can show that the ith node of the conjugate momenta is proportional just to a linear infection state, okay, for delta small still, okay? And so since S is given roughly by this is going to depend on quadratic for the, for the extinction case. And for different kinds of switching, you'll get different kinds of results. So you'll get a cubic. Okay? Then what you can do is you can go in and just expand the x and the p's in terms of this and just use regular perturbation theory. So you do that, and then to order delta squared, you get this result in terms of the equilibrium points for x and p. And so these are left and right eigenvectors of the connection matrix, and you can sort of see how these cubic terms and quadratic terms will come about. Okay? So to finish it off, what we do, we use a trick by Mark Newman from network science. Okay? And so the idea is that you can take the degree distribution and write it in this form, and then you get this kind of result. Okay? So you find out that these particular ratios of the low order to high order distributions in degree, okay, change the action. And since it's in the exponent, it gives you very large changes in the distribution where you're looking at different moments of degree distribution. So that's pretty cool, we thought. So what does it look like? So we want to project our plots of what the optimal paths that are given here in terms of the high, you can think of these as high connected nodes of infection versus low connected nodes. And so here for the high school network, the green line is the forward dynamics, that if you took this extinct state and just perturbed it a little bit, it'll go this way. It's to show the non-reversibility of the extinct optimal path, which is given by this blue line here. And the histogram is just given by Monte Carlo runs that we've normalized. Well, not normalized, I guess, but to illustrate that you're lying along the peak. This optimal path lies along the peak of the distribution. Okay, so we can look at the switching networks here as well. So we have these paths here, but here, unlike this one, which goes from the endemic state directly to the extinct state, here the switching is going through some saddle point before it switches. So here's another example to show if you have a very homogeneous network where everybody has 6 connections, okay, that if you just use the nodes only in your mean field, you get this purple line here, okay, which is off from what the PDF is from the numerical Monte Carlo's simulations. And if you include the link effects into the mean field, then you start to see very good agreement, much better agreement. So it's important to know what your mean field is and how you choose it in order to do accurate predictions. And finally, you consider multiple noise cases. So Mark and I and others have considered this problem where we've added, in addition to the Poisson type of noise and all these discrete state systems, we've added external noise here that's continuous, okay, and Gaussian. So we've got a parametric driven noise case here. And so you can ask what the shape of the noise is along this path, which is given by the red. And these are computed from the numerical data. So we do OK here. It's not perfect, but that's OK. OK, so the large deviation theory allows us to look at mixed noise cases, discrete and continuous together. OK, so what can you say about how these diseases go endemic? So we want to look in detail at some of these paths. So again, we look at the high degree nodes versus the low degree nodes. So we're take this high dimensional problem, we project it onto this plane, and then we look at varying this parameter, beta lambda, and the distance increases away from bifurcation as you go down this curve. So the red curves are those that are going to extinction from the endemic state. So here it's almost linear, okay, like I told you. Near bifurcation, it's going to look linear. Okay? And you start to see this 3-part nonlinear effect. So what's going on here? So you're starting at the endemic state. Noise is starting to cause the low order nodes, okay? They're changing more rapidly here, right? So it starts to change those first. Those drives those nodes extinct first. And then the high degree nodes start to change. They start to dominate. So most of the high degree nodes are starting to disappear. But there's an end game in order for it to go extinct. This is why extinction is so tough. It's because you have all these other nodes that are kind of sparse, and you can't get rid of them. So there's a chance of reinfection. So this was done for a power law network, okay? So here you can see the effects of what the degree are doing, right? Again, you have this, you can actually analytically analyze some of these things. But what's important here is, again, you have this three-part path to extinction, and it looks different for different values of k. So these curves are increasing k to the right, so it's almost linear here, and then it develops these nonlinear factors as you get further away from bifurcation, okay? And that's why the local analysis, you can't push beyond that, the bifurcation. So this is what it looks like if you sort of project things. So you sort of have these high degree nodes and low degree nodes, okay? So the low degree nodes on the outside start to go extinct first, okay? Then these large red dots here start to go extinct, and then you're left with the nodes that are on sort of the outer rim here that start to finish off the process. Okay, so that's what the theory gives us. So then you can ask, okay, what kind of time scales are we looking at here for the networks? So here's curves for different kinds of networks. I won't go into all the details, but essentially what we're assuming here is that there's no explicit independence in the action. Okay, so the size of the population here is not taken into account. But when S gets large enough, they all go to some slope 1, okay, which is what we expect. Okay, so it's set by the action, but you can actually do more if you look at data. So this is data by Derek Cummings, one of our collaborators, from measles in Thailand, in one of the Thailand processes, as a function. So it's the number of 0 cases that are reported as a function of time. And if you pull back and squint hard enough, you see that it's exponentially dependent on the population size. Okay? So it turns out that in general, for these populations, even in general networks, we find out that the action is directly proportional to the size of the population. Okay? For this particular case where we have noise that's also induced externally to this parameter that's Gaussian, we actually can compute this as a function of the noise intensity, and we do really well here. The theory is in red, and the Monte Carlo simulations are the dots. And finally, we can see something similar to a crossover effect. Okay? So here, where we have no hubs, and as you increase D, the external noise intensity here, you find out that you start to approach this particular line, right, which is all Poisson-based. Okay? But when you have just hubs, right, when you're in this process, we have like a power law network or a scale-free network where the hubs are sort of dominating here, you never really approach this line here as D goes to 0. Okay? And so this is an extension of some of the earlier work that Mark Dickman and Laura Billings and I did back in the day. Okay. All right, so essentially, you have localization in the network, so it's causing the time to depend on the log of the time to extinction to depend on n, and it's only reached asymptotically, and so you get this crossover, okay? And when D is not 0, you never really see this. Okay, so I've told you about the paths. Now how can we use these for control? Right, so there's a big push to try to bring disease down as fast as possible. Okay, so let me simplify the situation and just consider a bimodal network. So most of the nodes here have low degree, 5. Okay, and 10% have high degree of 50. So who are you going to target in order to bring the system down the fastest? Take a guess. Low degree, high degree nodes? High degree, right? Right? So let's check. So high degree, okay, so what I'm going to do, so this is the recovery rate. I'm going to add a parameter here, W, that is going to be some fraction that's going to tell me, okay, I'm going to vaccinate high degree, right? So when W is 1, I'm just going to vaccinate only high degree nodes. When it's 0, just low degree, okay? So here are the results. So here is W on the x-axis here, and this is the action, okay? So everybody has written papers about, let's get the highest guys. Look for the highest degree nodes, and that'll do it. and bring it down to extinction the fastest. But in fact, as you increase the strength of your control, what happens is that you develop a global minimum that's nowhere near the high degree nodes. Okay? You have to remember that this is going to go in the exponent here for the distribution. Okay, so if I look at just maximizing my treatment rate or minimizing my endemic state, right? Suppose I'm trying to maximize most of the population. So I target 90% of the low degree nodes. That's over on the left. Okay? Excuse me. If I want to minimize my extinction time, well, I should say minimize my distance to the bifurcation, I'm over here. Okay? So I'm trying to target these high degree nodes, but these squares here are at the global minimum. So there's a mix, right, of low degree nodes and high degree nodes. And that's because you always have this end game of trying to figure out who to target at the end, which are mostly low degree nodes. Okay? So you can see what happens for different factors here if I plot the log of the extinction times versus this W, and then I look at just two different control factors, right? So I get a huge exponential change in a prediction of what the extinction times are. Okay, I said that. Okay, and we did this also for switching. So we can enhance or retard switching. This is based on some work by Smilyansky and Dickman by just adding the constraint into the control problem using another Lagrange multiplier. Okay, so, but you can see the papers for that. So finally, I want to talk about adaptive networks. Okay, so most of the networks that we've talked about have static connections. So I want to consider the following problem. I want to consider the problem where everybody has perfect information about everybody in the room, but if you are connected to an infectious individual you know, then you're going to change your rewiring to somebody who's non-infectious. So it's the disease avoidance, all right? So you're changing your behavior in the presence of a threat, okay? So what we're going to do is model that as susceptible nodes that are cut edges with infected neighbors. And so the idea is the following. So you have some network and you have an example of an infected connected to a susceptible individual. I'll cut this node, and then I'm going to rewire this guy to this one. Okay? And I'm going to try to keep the average degree of the network roughly constant. Okay, so certainly you expect it to speed up extinction, but how does it do it? Okay? So this we puzzled over a long time. So this is a function of this rewiring rate, this W here, which is the rate at which I'm cutting links and rewiring. Okay? And so as soon as you turn on rewiring here, the log of the extinction time drops precipitously. Okay? So these two curves here are different degrees. So you can think of the blue dots as a more homogeneous network, and the green one is more heterogeneous. But in both cases, you get this appearing of a discontinuous jump that's huge. Okay? And we wanted to understand this because it's significant. So what we did was we looked at the degree of the susceptible nodes. Okay? So we look at the fraction of the degree of susceptible nodes. So when there's no rewiring, you see that the mean of the degree is hanging around 20. It's roughly Gaussian. As soon as you turn on it on the rewiring to 0.001, very small, right? You see this pinch effect where the degree becomes even more homogeneous, and that drops the threshold at which extinction occurs. And so you get a faster response in the network to this adaptivity. Okay, so I just said that. It becomes more homogeneous. Your network is closer to threshold. That's kind of known in the network science community. But this is the first time where we tried to understand what the degree of the adaptive network is as a function of time, and it's a mess. Okay, and so this is our hypothesis for why why you have these precipitous jumps in the extinction times. Okay, so you can ask, well, what about the size of the epidemic? Maybe that has a role to play in it, right? So if it's a big epidemic, it's harder to bring down. Okay, maybe it happens faster for smaller epidemics. But what we did was we fixed the epidemic size, okay, and we did the same thing. And we asked what the probability of extinction is as a function of the fraction of nodes. And so So this is the case with no rewiring. And again, as you increase the rewiring, the probability of going extinct goes up. OK, so let me sum up. I'm in good time. So OK, I told you what our prescription was for predicting these large changes in discrete stochastic networks. OK, we've thought about how to construct these mean fields. Sometimes you can do well with just nodes. Sometimes you need nodes and links. Okay. For general topologies, okay, we certainly found new scalings that are based on the topology of the network, at least near bifurcation. So we've been able to construct the optimal path. We've looked at the distribution of the fluctuations as well as extinction times, which are observables. Okay, and we've connected these properties of large deviations to the topology. We think that's the most important thing we've done here. Okay. The control we've looked at by leveraging these fluctuations. Since we know what the optimal path is, we can actually compute how best to target the population on a general network. Okay. And we've optimized the probability of fluctuations. It's definitely not a matter for local analysis. You have to compute these large heteroclinic or instantons in very high dimensional spaces. And it does require model reduction, and we've come up with some schemes for that. And even small adaptivity will increase this exponentially, the likelihood of large fluctuations. And in addition to Jason, a lot of other people have helped with us on this particular project, and I thank you very much. So I have some time for some questions. Yeah. Yeah.
You know, when you were asking about whether to attack high degree nodes,
right.
You had a model with two parameters. I didn't quite get it.
One's the strength, right. Right. So, right. So what you're doing with the gamma controls the amount of recovery rate. Sure. Oh, it's up here. OK. Yeah. So gamma controls the recovery rate, where W sort of controls the fraction of the high degree nodes that you're going to target. OK? So the stronger the gamma, the faster the recovery. So it's treatment.
Shouldn't there be some also parameter to distinguish where to put the threshold between high degree and low degree?
Well, that's what this is sort of telling you, that you're splitting this up, right? So if W is 1, you're all high degree. If W is 0, you're all low degree here. OK? All right? So we think of it as the fraction of high degree nodes here. OK?
The other little question, perhaps I misunderstood, but you said something about different mean fields having different epsilon, which is like one of the noise. I didn't quite get what that was early on. You said that.
Yeah, I mean, it's how you put your, where your noise comes in. So we just introduced, it was sort of a general parameter that we just say that, your mean field is going to be governed by, it's going to generate some sort of small amplitude noise. Okay, that's all. I mean, the mean field, when it's restricted to the noise case, is deterministic. But off that, yeah, I might have misspoke, right? But off that, the noise is going to push. So epsilon is just a generic small parameter. I may have misspoke there. OK.
I wanted to ask, when you are saying about the bifurcation is for a single node for the whole network. If this is for the whole network,
right.
It's one situation, and then there is probably one soft mode, not many. If this is for a single node, then there are many soft modes, but probably at a different time.
OK. Right. I see what you're asking. But no, this is for the whole network, OK, for one thing. OK. And it's possible that, I mean, it's a steady state, right, at the bifurcation point. OK. And so it is possible to have, different scalings. Okay, time scalings, if you look at the linearization. So you could have modes that damp down really fast, others that are slow. And then you have a multi-scale problem. And I think the next speaker is going to talk about multi-scale behavior. But yeah, I mean, we don't look at that in terms of the actual instability as how it comes about and how it plays against the extinction times, right? The only thing we know about are those left and right eigenvectors. And that contains more about the degree distribution near equilibrium than the actual time for each of these modes.
Right, but after all, you then just have single, slow variables.
Of course, if you have a distribution of rates, of course, absolutely, I agree with that statement. Yes.
In the case when you're talking about a random network,
right?
What is the setting that you actually work with? The setting where there is a randomly looking network, but it's a single realization, or you somehow, at least mentally, consider different realizations of the same network and average your final result over these realizations? Which of
the latter. So we do, yes. So we look at realizations of the network. You have a distribution that we want. We run like 50 realizations, but a lot of time computations, right? Times to extinction computations on each one.
Okay, but then I have an additional question. If you essentially have a distribution of initial conditions, you need to take into account the sort of cost what of the initial condition in the calculation of the actions. You essentially optimize the sum of the two. Is it what you did? The sum of the initial costs, quote unquote, and the dynamical actions that you were talking about.
Okay, so yes. So we do prep the system as best we can near the endemic state. Okay? That's the initial condition.
But it's random.
It's not entirely random because then you're far away from the state at which you're leaving, right? So we prep it so that you're once the system dynamics start, it's random, of course.
The dynamics is random, but the
yes.
initial condition,
you have to
said that it's random. Now I'm saying that it is essentially deterministic.
It's
which of the two?
No, but yes, the whole network, it's because it's a Poisson-based network, right? You're changing things in time, right? The states of the system are changing randomly, right? As the system is moving along, but you always have to start in around the neighborhood of the endemic state.
So
otherwise,
no randomness in the initial condition.
Not necessarily.
Okay.
But right, yeah, we have to prep it because that's what our goal is, right? We're measuring the time from something that's near the endemic state to the extinct state. So what we do is once we prep it, we know we're not actually on the state for any given network. So we let the system relax for a bit and then watch it continue. So it relaxes to the endemic state and then we start the clock. Okay, thanks.
Okay, so first of all, let me thank David and Gregory for inviting me to this workshop. So I'm really glad to be here. And thank you for staying to this last presentation. So it will be about time-dependent active micromereology in dilute colloidal suspensions. And you will hear in a minute what this is all about. But before I actually do this, let me just tell you what I'm usually known for. So I've spent many, many years on anomalous transport in cellular crowding or in porous media like the Lorentz model. I actually come from the glass transition, and I've left this field after my PhD for many years, since my PhD advisor told me you have to find your own topic. And so after some more than 10 years, I felt that this field didn't evolve a lot, so I can come back. I'm interested also in biofilaments and needles, and recently also in active particles, so the systems far from equilibrium, but I'm also interested in intracellular transport. Okay, so I can do it like this. So here's the setup. So we have a colloidal suspension, say of hard spheres, at some packing fraction. And so the suspension is in equilibrium. And at a certain instant of time, I start to pull at one particle. And I'm going to pull very, very hard on this tracer particle. And the questions that we are going to ask is, what is the time-dependent velocity of that probe particle? And what are, say, the fluctuations of this? And the goal is actually to provide an exact solution of this model system at the price of having it at a dilute packing fraction. And so this system is one of the few instances where you can solve for the complete dynamics of a strongly interacting system. And I try to convince you that the dynamics is far from trivial, but contains basically the whole plethora of non-analytic dependencies, as some of you know, for equilibrium systems. Okay, so what kind of question do we want to ask? So for example, in equilibrium, you would be interested in the intermediate scattering function. This is in essence the Fourier transform of the probability distribution, say that a single particle is displaced by a distance r in time t. These intermediate scattering functions, as the name suggests, can be measured directly in scattering experiments, say light scattering experiments for colloidal particles. You can view this quantity also as the characteristic function, since it generates the moments. So by taking derivatives with respect to this wave number, you can generate, say, the second moment, the mean square displacement. In equilibrium, the first moment is not very interesting because of symmetry reason. This is just vanishing. So there's a different characterization of the mean square displacement, which is the velocity autocorrelation function, which I define here in this colloidal setup just as the second derivative of the mean square displacement. There's a related quantity, which I call the time-dependent diffusion coefficient, which is just the first derivative of this mean square displacement here. Okay, so what is known about the system in equilibrium? So in equilibrium, this system has been solved in first order. I hope you recognize the movie. So in first order of the density, the system boils down to solve for the relative dynamics of just two particles. And this can be done. And in particular, I'd like to point out here the velocity autocorrelation function. This can be solved in the Fourier domain. And you see in lowest order of the density, this is just a constant, which tells you in this Brownian dynamics, velocities are killed instantly. And the effects of the interaction are here in this proportional to this packing fraction. It's first order in the density, so the series stops here. And there's a non-trivial frequency dependence. In particular, this frequency dependence contains square roots, that this is non-analytic. So if you work out the lowest order term of the series in the frequency, you arrive at the term omega to the 3/2. And if you transfer this back by Taubert theorems to the time domain, you arrive at persistent correlations. So the velocity autocorrelation function decays only like a power law. Here it goes like t to the minus 5/2. And there's, of course, this other class of persistent correlations in interacting particle that have been mentioned in the last talk. These are these so-called Alder tails. This is because of momentum conservation. When particles interact, the momentum can diffuse away only slowly. Here's no momentum conservation because I have Brownian particles, but I have particle conservation laws. And still, in these systems, this particle conservation law leads to persistent correlations in equilibrium. And this has been predicted many years ago by Hanna and Hesse or Agassi-Fleischmann. There's also a related paper by Oberfelderhoff. Okay, actually I came across this problem many years ago when we were interested in the Lorentz model, because in first order of the density, it doesn't really matter if all particles move or only one particle moves. And we were interested at that time in the percolation transition of the Lorentz model. So in the Lorentz model, that only one tracer particle moves and all the other particles are fixed. And my PhD student generated the velocity autocorrelation function in simulations. And we were wondering if she could see these tails. Yes, she did. And then she did something which she was not supposed to do. She divided the velocity autocorrelation function by the density and found almost data collapse, although the density is not low. And I thought at this point, wow, this is excellent news, because this means I need to calculate the velocity autocorrelation function only in first order of the density. This is something that I can do. And it turns out the calculation is very similar to Hanna and Hess. And so this was for 2D, so the exponents are very different, but anyway. Okay, let me show you now simulation data for the 3D system for dilute Brownian dynamics. And you see this is the theory by Hanna and Hess. And these are the simulation results. And you see, indeed, there's this long time tail of t to the minus 5/2. There's actually also a tail for short times. This has something to do with the hard interaction. This you can call the skin effect if you want. Okay. Okay, now let's go to the real program. So now I want to follow Hanna and Hess and look at this problem of pulling where one tracer particle is pulled out of equilibrium, and the key quantities are the velocity, stationary velocity, time drift velocity, and the fluctuations. Okay, why would that be interesting? Well, first, there's the fluctuation dissipation theorem that tells you the linear response should be connected to the equilibrium dynamics. So if I look at the deterministic linear response, so linear in the force, then this should be given by the fluctuations in equilibrium by the velocity autocorrelation function. And indeed, you check easily in the stationary state at the long times that the velocity is just diffusion coefficient divided by kBt times the force. So this is called the Green-Kubo relation. Okay, kBt mediates between fluctuations and deterministic response. And you see also that without any interactions, if you have only a single particle, then the velocity response is instantaneous. So the velocity of a fluctuating velocity decays instantaneously. Now I can do the following. I can ask, how fast do you approach the stationary state? So I convert basically this integral, and you see I integrate over large times of this velocity autocorrelation function, but this decays only like 5 to t to minus 5/2. So I expect by linear response that I approach the stationary state only algebraically like t to minus 3/2. Okay, so what happens if you do finite forces now? Okay, so what also has been worked out is the stationary case. So I define a stationary mobility by dividing just the stationary velocity by the force. The result will depend on the force, and it's a good idea to measure things in a dimensionless number, which is the Pecklin number. So this is just a measure for the dimensionless force. And there are reasons to divide it by 2 kBt, not by 1 kBt, which I don't explain here. So in particular, if the Pecklin number is 0, and if you are at infinite dilution, you would have just the Stokes mobility. And to first order in the density, the mobility has been worked out in equilibrium. So for Pecklin number equal to 0. And by Squires and Brady, some more than 10 years ago, they have generated an asymptotic expansion of the stationary mobility in terms of the Pecklin number. And the following is remarkable. So what I added to their calculation, I put here absolute magnitudes, since it should not matter whether you pull to the right or you pull to the left. So this tells you that this expansion here is non-analytic. So now most people are, oh, this means generally if I perturb a system, then beyond linear response, the response is non-analytic. So this is kind of dangerous. Okay, so here are now simulation results both for the liquid, for the suspension, and I told you in first order of the density, it doesn't really matter if everybody moves or only a tracer particle. You can do the same for the Lorentz model. And the questions I want to elucidate now is, where do these non-analytic terms originate from? And what do they have to do with the long time tails that I showed you before? And how can you do numerics with something that is singular already at Pecklin number 0? Okay. So here's the setup. So what we need to do is, in lowest order of the density, I just need to consider 2 particles and only the relative motion. And the governing equation is rather simple. So psi is the probability that starting at a relative distance of r prime, that I observe a relative distance of r at time t, and it started at time 0. And the equation is just this advection diffusion equation. So here is diffusion, and since it's relative diffusion, the relative diffusion coefficient is actually twice as high. Then in addition to this, there is a drift term which tries to tear this pair of particles apart. So this is an advection diffusion equation. I start this from equilibrium, so so the particle is where it is, but there this maybe there I have to this just means that the initial separation has to be larger than the interaction distance. And of course, there's a boundary condition that once these two particles touch, that there is no probability flux inside. Okay, so the first thing that I do is I take, so what I want to calculate is the generating function or characteristic function of this relative motion, and I do this by basically integrating over the initial position and averaging over the initial position and integrating over the final position modulated by this exponential here. So this, once you know this quantity, you know you can generate the moments. Okay, so here comes the technical slide. So again, I do now a Fourier transform with respect to time, and I a Fourier transform with respect to the initial condition. And then my advection diffusion equation looks like this. And here I subtracted the solution without interactions. Okay, so this is the equation. And the key observation for this equation is anisotropic, but I can make a nice trick. I can multiply, I can make an ansatz, some function times this exponential. And then it turns out that this function just satisfies a Helmholtz equation. So by this gauge transformation, I transformed this advection diffusion equation to just a Helmholtz equation, which I can solve easily. The price is now that I have this complex wave number that encodes both the frequency and the force, that is the Peckley number. So this equation here is easily solved on a formal level, so you decompose into Legendre polynomials, and the solution of the radial equations are just some spherical Bessel functions. And all you need to do is you need to determine these coefficients here. So these coefficients are undetermined. They depend on the wave number, on this complex new wave number, and the Peckley number. And you have to put them into the boundary condition. Okay, that's what I'm going to do. So, and here comes the problem where I cannot do only analytics. So since the original problem is not spherically symmetric, this means that all angular channels couple, but that couple in a kind of boring way, namely, so this is a tri-diagonal matrix, so each angular channel couples to the channel below and above. And you see in equilibrium, so if I cancel these two terms, the Peckley number is 0, I arrive here at the solution immediately. So what's interesting is now, so this term here is known. What's interesting is now you can do a perturbative approach in the Peckley number for fixed complex wave number, and you don't expect anything singular here. Yeah? So there's no reason to believe why this matrix equation should be singular or whatever. At the end, we want, it's customary to interpret this result in terms of a propagator. So this propagator here, this term here, is basically the free diffusion advection motion, and everything that's hidden in that comes in by the interaction is hidden in the so-called self-energy. And this is my formal solution, first order into density. So at the end, to lowest order into density, I just have to multiply the self-energy with the number of interacting pairs. Okay, so I have a formal solution now. Let's try to interpret this. Say for the mobility, so that's the mobility in the frequency domain. You see there's an instantaneous reaction for the infinitely dilute system, and all the interacting terms are hidden here, linear in the density. And you can check that this solution has only even powers in the Peckley number for fixed kappa sigma. So where does these non-analytic terms come in? Well, the price of this gauge transformation was that this complex wave number is a square root of a combination of frequency and Peckley number. And the square root is analytic everywhere except at the origin. So the origin, this is the origin where everything becomes complicated. So in particular, if I go to the stationary case, that is frequency 0, you see my wave number becomes the magnitude of the Peckley number. So this generates the terms found by Squires and Brady. If I put the Peckley number back to 0, I arrive at the square root of the frequency. These are the long time tables found by Hanna and Hess. So this theory kind of contains both. So these these long time tails in the linear response and this non-analytic dependence of the response coefficients are kind of two sides of the same coin. Okay, and I have a physical interpretation. They actually originate from this algebraic decay and the return probability of the diffusion problem. And actually, we did something similar on a lattice, and that's how I got in contact with this community, say with Olivier Benichou or Carlos Monichia Manastera. So on a lattice, you can do a little bit more. You can solve this not only formally but exactly, and there the scenario is the same. But this is now off lattice. This is the real thing that you can, in principle, measure in a lab. Okay, let's give a physical picture here now. What happens in time? So we, as a side result, we get the pair distribution function in the frequency domain. So the upper one are simulation results as you switch on the force for the pair distribution. And you see initially the pair distribution function is almost spherically symmetric, but as time evolves, probability piles up in front of the pole tracer and is diluted behind. And if time progresses, there's basically a trailing weight here. And this is the analytic result, which is basically the same thing. Okay, so probability piles up in front of the particle. Okay, let's now look at numerical results. If I just evaluate my solution, this is now here the approach of the mobility to its stationary value. And I told you that linear response, you expect that this goes like a power law t to the minus 3. This is true for Pecklin number 0. But as soon as I switch on the Pecklin number to any finite value, you see that this power law is left, and I approach the stationary state actually exponentially fast. And what's even more interesting, this is kind of, so this is a surprise, and I don't have a real explanation for this. There's a sign change. So if you switch on the force, first the particle reacts with the spare mobility, so you don't see the other particles. Then you slow down because you start interacting with the other particles. But at a certain instant of time, you speed up again to reach your terminal value. Okay, so what's interesting now is what is also a result of this analytic solution. There's a divergent time scale that separates, so for small Pecklin number, there's a divergent time scale that separates the linear response behavior, that is the regime where linear response is qualitatively correct, from the truly non-linear regime. And this time diverges as the Pecklin number goes to 0. So you see in this equilibrium regime, you just decorate the tail by an exponential. But there's a second regime where you have the sign change here, and again, something approaches exponentially fast the stationary state. Okay, we can do more. So the mobility characterized just the mean motion of the particle, but you can do more since in principle we have the characteristic function, and you can go to higher and higher moments. So here we did this for the variance. So that's the variance along the force. And equivalently, we use the time-dependent diffusion coefficient, which is just a derivative of this variance here. So again, what do you expect in equilibrium? In equilibrium, you expect that this time-dependence diffusion coefficient decays algebraically. Well, the reason is, again, that the time-dependent diffusion coefficient, if you take the first derivative, this is just the velocity autocorrelation function, but this has been shown to display these non-analytic dependencies. So also this time-dependent diffusion coefficient should approach algebraically a stationary value. And actually it should do it in a monotonic fashion, since in the Smoluchowski setup, interaction of particles can slow down the dynamics only. Okay, this is now the result for the force-induced contribution of the diffusion coefficient. And the first thing that you can see is by making the Pecklin number, that is the force, large, I can make these fluctuations as large as you want. Second, if I look at small Pecklin numbers, then I get also an expansion for this time-dependent, for the stationary diffusion coefficient, and this again becomes a non-analytic function in the Pecklin number. So this is not a surprise after what you've learned for the mobility. Okay, this now shows if you drive harder, then your diffusion coefficient, this is now the time evolution of the variance, and you see that you start from this initial value, and if you drive hard, then this diffusion coefficient can become large. So if it becomes large, then there is an intermediate window of superdiffusion, right? So there's an intermediate window of superdiffusion. This is shown here if you look at the variance. So initially, you grow with the variance. For long times, we have a saturation, so the time-dependent diffusion coefficient becomes a constant again. But in between, you have a growth of the variance that is faster than linear, and you can make your guess what it is. An indicator would be to take this local exponent, so this is in essence just a logarithmic derivative of the variance. And your first guess may be it should go like alpha is equal 2, which would be ballistic motion, but this is not true. This exponent actually becomes larger than 2, and it approaches values of 3. And we saw this earlier for the lattice, and when I saw this first, how can that be? How can this variance grow faster than ballistic motion? And there's actually an easy argument that we came up with. So these figures are here for the lattice, where the simulations are easier, and you see that you can make this window of superdiffusion as large as you like if you pull harder and harder. And the argument then is the following, and that's actually where the large fluctuations come in. So if you pull really, really hard, and it's easier to visualize this in the Lorentz setup, where you have one tracer and all the others are fixed, is what happens if you switch on the force? Well, if you pull really hard, you can forget about the diffusion, and your particle will just move straight. How long will it move straight? Until it bounces hard into another particle. And then it will basically stop, and it takes some time to move around the surface to keep going. So I can reduce the motion to a one-dimensional model, and this model is very simple. I can write this down in one line. So the particle moves just straight until it bounces into a particle, and you have to use the probability distribution of what is the distance to the next particle. So this is the bus stop problem, basically. When does the next bus come, and this is a Poisson distribution. So this sits in here, and the only parameter I have in here is the mean free path length. So this will go like 1 over density times some effective scattering cross-section, and this, I call it effective because it's not the geometric cross-section. You have to hit really hard in order that you get blocked and not just slide around an obstacle. And with this simple model, you can derive within 2 lines that the leading behavior is indeed t to the 3. So this distribution of hitting an obstacle for the first time immediately gives you this t to the 3 as the true asymptotic limit for superdiffusion in this intermediate time regime. Okay, that's it. So I've shown you the response to a step force, the time-dependent mobility. You can do this perturbative scheme in the Pecklin number as long as you keep this complex wave number fixed. And the non-analytic terms emerge at infinite times because these limits, Pecklin number to 0 and frequency going to 0 don't commute. Actually, there's a nice interpretation, and since I have so much time that I can give it to you, how this actually comes around. So in the equilibrium system, these power law tails originate from the power law decay of the return probability. So the return probability would be a Gaussian, but the Gaussian has a normalization factor, which is 1 over the square root of the variance or something like that. So in 3 dimensions, so this would be t to the 3/2. So in this power law feeds into the power law of the velocity correlation function. What happens now if you start to pull your system? Well, if you pull your system, the return probability will still be a Gaussian, but a shifted Gaussian. So the probability to return to the origin will not decay algebraically, but exponentially fast. Yeah? So this is the mechanism how you kill the long time tails in the equilibrium system, and the approach is exponentially fast for any driving. But there's this interesting intermediate, or this interesting regime where the limits don't commute, and there's lots of physics in it. Yeah. For the lattice system, we've worked that out recently, also for the three-dimensional lattice. The next step would be, can something like this be done for the time-dependent viscosity? And more generally, we would be interested in, can one say something mathematically sound on the properties of response functions far from equilibrium? Yeah, and this is, of course, totally open field. Yeah. Okay, that's it. Thank you for your attention and look forward to your questions.
Yeah, thank you very much. So we have time for questions and comments. Yeah, Ralf.
Feeling. Thomas, beautiful. Your feeling, if you were trying to implement this in a real experiment, and we say we have colloidal particles, micron-sized particles, what effect would you have when hydrodynamics comes in?
This is, of course, an important comment, because in a real system, you have these hydrodynamic tails, these Alder tails. And so what we did, I mean, we cannot solve it, so we cannot solve it, but we can cheat. And the cheat is the following. So rather than doing it with a bare diffusion coefficient, we just use a frequency-dependent diffusion coefficient that takes into account these anomalies. And what you see then is, what happens is that you have a crossover from this in equilibrium, this anti-correlated T2 minus 5 half to positively correlated T2 minus 3 half. So there's a crossover, but there's a separation of time scales, because my effect here comes from the interactions of colloids. The effect of hydrodynamics is interaction with the water molecules. So that's where the separation of times come in. And if you put in numbers, so I spent some time also on hydrodynamic long time tails. If you put in numbers, there should be a window of at least 2 or 3 decades in between, where you should be able to see that. Nevertheless, I don't recommend an experimentalist to do that experiment, since you see, even in equilibrium, you see here the velocity autocorrelation functions, and velocity auto are taken by taking twice the derivatives. So that my postdoc could actually do this in a simulation is because he invented a really brilliant scheme how to simulate this in dilute systems. How do you do a simulation where basically most of the time you have only noise and almost never an interaction with particles? Yeah? And he found a very interesting scheme how to do that. Repeat that, please.
You get negative differential mobility when you increase the force at high densities? Because I noticed that the signs of the coefficients of the Peclet number is...
So we haven't looked at that, but we did this on the lattice. On the lattice, this can happen. Yeah. So, and Olivier has studied this in more detail for a related model. So this can happen in principle. Yeah. It happens already on the lattice in linear order of the density. Yeah. Yeah. I do have plots, not for this one here, but I do have plots where actually the velocity goes down again, and it goes to 0 again if you pull really, really hard. And on the lattice, you can understand this if you have hard obstacles. Basically, if you, I won't do this here because you bump into the same obstacle all the time, and you never get forward unless you make a step aside. Yeah. So pulling harder doesn't help, and this is your negative differential mobility. Yeah. But you see, I have this sign change here, which is, I don't have an explanation for that, but this does not happen on the lattice. So the sign change does not happen on the lattice.
Did you check the non-Gaussianity of this process?
No. Okay. So we did this on the lattice. Yeah, on the lattice you can do this because on the lattice you can solve for everything. Here, for non-Gaussianity, I would need the next higher cumulants. I need the fourth cumulant, and since the probability distribution is skew anyway, I don't really know how to define a non-Gaussian parameter. So what we did is for the transverse motion on a lattice. Yeah, so you can ask what are the fluctuations transversely to the force. So there it's kind of easier because the first moment is the mean square displacement, and then you have the fourth moment, and out of this you can construct a non-Gaussian parameter, or what my students did is actually a non-Scalem parameter. So on the lattice you know that the distribution should not be a Gaussian but a Scalem distribution, and you can calculate the deviations that are induced by the density from this trivial empty lattice. Yeah? So in principle it can be done. It's not Gaussian. It's not Gaussian. No, it's not Gaussian. And this I don't know. I haven't done this here, but it's definitely skew. Yeah, so I'm pretty sure there's no reason why it should be symmetric. So I'm pretty sure, but I haven't done that. Yeah.
Okay. Any further questions? Yeah.
Was a bit also about these variance growing faster than ballistic.
Yeah.
So, I mean, if velocities are bounded, you cannot have that. Does it mean that here your particle is accelerating?
No. So that was precisely my confusion. So the reason is indeed that you have a distribution of stop times, basically. Yeah? So the distribution when you stop is exponentially distributed. So I can show you the probability distribution again, and it's amazing that you can work this out. That you can, from this distribution here, you can work out that you have this t to the 3. Yeah. So it's not good enough. So if you say, so it's not a bimodal thing, so that you say, okay, some particles move with constant velocity and others are just blocked. If you do this, then you arrive at ballistic motion, and actually I think you can, maybe you can even cancel this. So it's really because you have a distribution of the stopping events, which are exponentially distributed. Yeah. So it is counterintuitive, I admit. But we did this on the lattice, and there it's very easy to do, and you can do it also in the continuum with a little bit more effort.
Okay. Any more questions? Okay, so if not, let's thank all the speakers of the session again.